The more we look into the universe, the closer we get to where it all began. But there is a hard limit, the edge of what we can see, where light can't take the story any further. This trip isn't about ideas or theory, it's about the real measured limits that we've found with telescopes, particles, and signals that go back almost 14 billion years. We are going to look at 35 of the most interesting and little discussed edges of what science has shown us at the very edges of what we can see. These range from the last scattering surface of the cosmic microwave background to the faint glow of the farthest galaxies ever captured, to the whisper of hydrogen at 21.1 centimeters. The cosmic light horizon. A wall or barrier floating in space is not what we mean when we talk about the edge of the observable universe. Instead, we're talking about the cosmic light limit, which is the farthest away that light has been able to reach us in enough time since the beginning of time. The rules of science and the speed of light set this as the highest point that can be seen. It's not set by technology or telescope power. This horizon is so interesting because it doesn't just show us how far we can see. It also causes us to face the fact that the universe is expanding, which means that it is much bigger than its age would suggest. Picture lighting a fire in a place that is very dark. The glow keeps spreading out at a steady rate, lighting up more space every second. Now imagine that you are not holding the candle, but rather observing it. The light is made up of all the photons that the world has given off since it began 13.8 billion years ago. You might think that 13.8 billion light years would be the farthest thing you could see. But in a world where space itself expands as light moves through it, that easy calculation doesn't work. Because of cosmic expansion, those photons have been riding a moving walkway that's constantly growing beneath them. As a result, the current distance to the most distant observable regions is not 13.8 billion light years, but about 46 billion light years in every direction. That makes the observable universe a sphere nearly 92 billion light years across. This discrepancy is one of the most important insights in cosmology, a clear reminder that space isn't static but dynamic, reshaping distances as time ticks on. The cosmic light horizon is more than just a number. It's also a boundary condition in physics. We can't see past it with light, no matter how advanced our telescopes become, because there simply hasn't been enough time for signals to reach us. It defines the spherical bubble of information available to us, and everything outside it remains unobservable, not because it doesn't exist, but because its signals are forever beyond our reach. That makes this concept both incredibly simple, light takes time to travel, and profoundly humbling, because it means we'll never have a complete map of reality. This horizon also raises subtle distinctions that often get glossed over. For instance, the cosmic light horizon is not the same as the particle horizon, which refers to the maximum distance particles, like photons or neutrinos, could have traveled since the Big Bang. Nor is it the same as the event horizon of our universe, which defines the farthest distance from which light emitted now will ever reach us in the future. The light horizon specifically describes the limit of what we can observe right now, a snapshot of accessibility in cosmic time. The concept shows up every time astronomers publish record-breaking discoveries about the most distant galaxy or quasar. When we say an object is 13 billion light-years away, what we really mean is that we're seeing it as it looked when the universe itself was less than 1 billion years old. By the time its light has arrived, that galaxy has actually receded to a far greater distance, often tens of billions of light-years today. The light horizon is why these phrases about looking back in time are not just poetic, but literally accurate. Distance and time are inseparably linked when dealing with horizons. Horizons are not static. As time passes, the observable universe grows. Each new second allows light from slightly more distant regions to finally wash over us. In a sense, we are constantly discovering new slivers of the cosmos simply because time keeps moving forward. Yet, paradoxically, dark energy, the mysterious force accelerating cosmic expansion, also means there are regions whose light will never reach us. no matter how long we wait. So the horizon is both expanding and limiting at the same time, a cosmic tug-of-war written into the fabric of space-time itself. Even the cosmic microwave background, CMB, the afterglow of the Big Bang, is tied to this idea. Those photons have been traveling for nearly 13.8 billion years, and they represent the farthest electromagnetic wall we can see. Beyond them lies the true cosmic horizon, which can only be probed indirectly through particles like neutrinos or gravitational waves. The CMB, then, is not the edge of the universe, it's just the inner face of our current light horizon, a kind of fogged glass window that blocks any deeper electromagnetic view. In a more practical sense, the light boundary is what makes it possible for us to make maps of the universe. To figure out redshift, standard candles like type Ia supernovae, and baryon acoustic waves, we need to know how the horizon affects wavelength stretching and brightness lowering. Cosmology would be limited to simple distance calculations without this framework, and it would not be able to show the full scope of the past of the universe. Something very important that the cosmic light limit does is change the way we think about size. It's already hard to understand 92 billion light-years, but that's just the bubble we can see. The universe is probably bigger, maybe even infinitely bigger, but we can't know how much bigger it is beyond the horizon. It's not a matter of bad facts or not enough money. The way things are in the universe makes sure that every viewer lives in their own observable bubble, no matter where they are. The last scattering surface. If the cosmic light horizon is the edge of what we can see, then the last scattering surface is the picture that is closest to that edge. In the past of the universe, this is the time when the universe first became clear, letting photons move through space without constantly hitting particles. This event took place during a time called recombination, about 380,000 years after the Big Bang. The universe used to be a hot, dense gas, where light couldn't go very far without being captured and sent out again. Imagine living in a fog of glowing particles that never went away and made it impossible to see anything. After a short time, as the universe cooled, hydrogen atoms appeared, the fog cleared, and photons could finally travel without any problems. It is these photons that we now call the cosmic microwave background, CMB. The last scattering surface is not a literal surface in space, but rather a spherical shell in time. Because light from that epoch has been traveling ever since, every direction we look in the sky brings us to the same boundary. In practice, it forms a cosmic wallpaper, a nearly uniform background of microwaves that fills the universe. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB revealed itself as a faint but pervasive glow at a temperature of about 2.7 Kelvin, just above absolute zero. That faint signal is the afterglow of the universe becoming transparent, frozen into space itself. But this surface is not featureless. Tiny anisotropies, or temperature fluctuations in the CMB, represent slight differences in density and pressure across the early plasma. These ripples were the seeds of all future structure, galaxies, clusters, and voids. They are cosmic fingerprints left behind by quantum fluctuations stretched to enormous scales by inflation. When cosmologists study the mottled map of the CMB, they're effectively looking at the initial blueprint of the universe. Each cold or hot spot encodes information about conditions that existed almost 14 billion years ago, long before galaxies assembled. The recombination theory explains why this change happened so quickly. The temperature of the universe dropped as it grew bigger. It turned into neutral hydrogen when it cooled down enough for the electrons to link to the protons. The universe became clear all of a sudden because there were fewer free electrons scattering photons. Photons that were stuck in the plasma fog could now move freely, and they have been able to do so ever since. Because the universe is expanding, these photons are now stretched so far that they look like microwaves instead of light. The word last scattering comes from the fact that those photons had their last strong interaction with matter. Observing this surface has become one of the most precise tools in cosmology. Missions like COBE, WMAP, and most recently Planck have mapped the CMB across the entire sky. These missions measured not just temperature but also polarization patterns, giving us detailed insights into the density of matter, the geometry of space, and the relative amounts of dark matter and dark energy. It's thanks to these observations that we can state the universe is flat to within a tiny margin of error, and that dark energy dominates its energy budget. In other words, the last scattering surface isn't just a relic, it's the foundation of modern cosmology. The structure of this surface also reflects subtle physical processes. For instance, sound waves rippling through the hot plasma before recombination left imprints on the CMB. These are visible as a characteristic pattern in its power spectrum, peaks and troughs corresponding to oscillations in the early universe. Studying these patterns allows cosmologists to test theories of inflation and refine measurements of the Hubble constant. In this sense, the last scattering surface is not just a snapshot, but a highly detailed record of the universe's youth, written in light. It is important to understand that the last reflecting surface we see is actually a time horizon, not a space horizon. If you could stop the growth of the universe and go to one of those areas now, you wouldn't find a bright wall of plasma. There would be galaxies and stars instead, just like everywhere else. Photons from that time are the only ones reaching us right now, which is why the surface exists. The illusion is caused by the fact that light has a limited speed, and the universe has been slowing down over time. The last scattering surface is still a mystery, even though it is one of the most studied things in astronomy. The CMB cold spot is one of the most interesting. It is an area that is extremely large and cold, and it doesn't exactly fit what statistics would say should happen. Some theories say it could be because of a huge void in space, while others wonder if it's a real strangeness that points to new physics. In the same way, studies of polarization keep helping us learn more about reionization, which is the later time when stars and galaxies reionized hydrogen, making the clean picture that recombination gave us more complicated. The particle horizon versus event horizon. They don't always mean the same thing when they talk about boundaries. Each edge of the world is set by the kinds of messages that can and can't reach us. The particle horizon and the event horizon are two of the most important, but they are also often mixed up. Both talk about how little we know, but they do so from different points of view. One looks into the past, the other into the future. To understand why the visible universe is different from the rest of the universe, you need to know about them. The particle horizon is the boundary of what we can observe today. It's the maximum distance from which particles, including photons, have had time to reach us since the Big Bang. In other words, it sets the radius of the observable universe at about 46 billion light-years. This horizon is a look-back limit, defined by how long signals have been traveling through expanding space. If the universe is 13.8 billion years old, then why is this horizon so much larger? The answer is cosmic expansion. As photons traveled toward us, space itself kept stretching, carrying their source galaxies farther away. That's why the observable sphere is nearly 92 billion light-years across. The event horizon, on the other hand, looks forward. It's the maximum distance from which light emitted today will ever reach us in the future. Because of accelerated expansion driven by dark energy, there are regions of the universe whose signals will never arrive, no matter how long we wait. This makes the event horizon a limit not of current observation, but of potential future observation. If the particle horizon tells us how much of the universe we can see, the event horizon tells us how much of the universe we will ever be able to see. Current estimates place this cosmic event horizon at about 16 billion light-years, much smaller than the particle horizon. The contrast between these two horizons is striking. The particle horizon says, "Here is everything you can observe so far." The event horizon says, "Here is everything you will ever observe, even if you wait forever." The fact that the event horizon is smaller than the particle horizon means that galaxies we can see today may eventually slip beyond our reach. Their light, already en route, will arrive, but any new light they emit from now on will never cross the gulf to reach us. It's as though the universe is slowly pulling the curtains shut on much of what we can currently view. This is not just an academic difference, it changes the way we think about what will happen in the universe. In the case of scientists who study faraway galaxies, many of them are already doomed to become invisible in the future. Even though we can study them now, their signs will finally become too weak to pick up as the universe expands. It also changes how we think about the history of the universe. The particle horizon tells us what we can see in the past, and the event horizon tells us what part of space we will still be linked to as it gets smaller. Try standing on a beach during a storm to get a sense of the difference. It's like the space between the farthest waves that have already hit the beach. When waves hit the water, they can't get to land. This is called the event horizon. There are two boundaries, but one shows what has already come and gone, and the other shows what will never come. Another complexity is that these boundaries change based on how fast the universe is expanding. The event horizon wouldn't exist if the universe was still or slowing down. Light from everywhere would finally be able to reach us, but because of dark energy, growth is speeding up, which is pushing places apart faster than light can connect them. A hard event horizon is a line that can never be crossed. It is made by acceleration. The event horizon stays in place in a world ruled by dark energy. Measurements of these horizons also help refine cosmological models. For example, when cosmologists study the cosmic microwave background or galaxy surveys, they must distinguish between signals limited by the particle horizon and predictions constrained by the event horizon. Without making that distinction, we risk misinterpreting what edge of the universe really means. This is why clear definitions matter so much in cosmology. There's also an emotional component. The particle horizon feels like a triumph, a record of how far we've reached with light and matter. The event horizon feels like a loss, a reminder that much of the universe is already slipping away. Galaxies beyond the event horizon aren't just far, they're permanently inaccessible. Even with infinite time and the most powerful future technology, they will never be part of our observable reality again. The farthest galaxy observed. One of the most exciting milestones in astronomy is when a new record is set for the farthest galaxy ever seen. These discoveries are more than just numbers on a chart. They push our vision closer to the universe's earliest moments, offering a direct glimpse into how the first galaxies formed and evolved. Right now, the champions in this cosmic race lie at extreme redshifts, where their light has been stretched across billions of years by the expansion of space itself. For a long time, the galaxy known as GNZ 11 held the record as the most distant ever found. Discovered using the Hubble Space Telescope and the Keck Observatory, it sits at a redshift of about 11.1. That means we see it as it looked only 400 million years after the Big Bang, practically the dawn of cosmic time. What made GNZ 11 even more surprising was its brightness. It was already forming stars at a furious pace, showing that galaxies could build up faster and earlier than many theories expected. But GNZ 11's record hasn't stood unchallenged. With the launch of the James Webb Space Telescope in 2021, astronomers have begun peering even deeper into the early universe. Thanks to its infrared vision, JWST can detect galaxies Hubble could never see, since extreme redshifts push visible light into the infrared range. Already, JWST has turned up candidates at redshifts around 13 and beyond, galaxies shining only 300 million years after the Big Bang. These finds still need careful spectroscopic confirmation, but they mark the new frontier. Galaxies forming at the very edge of what we can observe. The challenge in confirming these galaxies lies in measuring their redshifts precisely. Photometric redshifts, estimates based on the color of light through different filters, can be misleading, sometimes mistaking closer dusty galaxies for faraway pristine ones. Spectroscopic redshifts based on the clear fingerprint of emission or absorption lines, are more reliable but harder to obtain for such faint, distant objects. JWST's NIRSpec and NIRCam instruments are now making those measurements possible, giving us unprecedented confidence in pushing records further back in time. What's most interesting about these early galaxies is how fully grown some of them seem. We thought that small, uneven groups of stars would slowly come together to form bigger galaxies in the first billion years. Instead, some of JWST's findings point to well-structured systems, large groups of stars, and maybe even disks. That has made cosmologists rethink what they thought they knew about how fast matter clumped together after the cosmic dark ages. If these big, well-organized galaxies were around just a few 100 million years after the Big Bang, then the processes of star formation and black hole growth may have worked much better than we thought. Studying these galaxies also gives us crucial information about the epoch of reionization, the period when ultraviolet light from the first stars and galaxies ionized neutral hydrogen, making the universe transparent again. The abundance and brightness of galaxies at high redshift directly shape how reionization proceeded. If there are more galaxies at these distances than expected, they may well have been the main drivers of this transformation, rather than rarer quasars. The record-breaking galaxies also serve as natural laboratories for studying stellar populations we can't see directly, like the hypothesized population 3 stars. These were the first generation of stars, massive, short-lived, and composed only of hydrogen and helium. While no population 3 star has been observed yet, their influence might be detectable in the chemical signatures of the earliest galaxies. Low metallicities, unusual spectra, and high star formation rates could all hint at their presence. The calibration of our cosmic models is another important thing that these finds have led to. The locations and light of galaxies at different redshifts help us figure out things like the Hubble constant, how dark matter clusters, and how well stars form. By going beyond the redshift limit, scientists check to see if the normal lambda cold dark matter, KCDM model, makes sense. If galaxies keep showing up earlier or bigger than expected, it could mean that we don't fully understand how dark matter behaves, the physics of baryons, or even how the universe is expanding. Each new record galaxy pushes the limits of current technology. Even JWST, powerful as it is, cannot see everything. To study galaxies deeper into cosmic dawn, astronomers often rely on gravitational lensing, where massive galaxy clusters act as natural telescopes, magnifying background galaxies. This technique has already revealed some extreme candidates, and when combined with JWST's capabilities, it creates the most sensitive cosmic probe humanity has ever wielded. But there is also a moral point to this, even in the realm of hard science. It's not likely that any of the galaxies we see are really the farthest. That's just how far away we've been able to find it so far. At that time, the universe must have been full of galaxies, many of which are too small or far away for us to ever see. Each discovery is like finding the brightest mountain peaks that stick out above the clouds and give a glimpse of a scenery that you can't see. In practical terms, the quest for the farthest galaxy is not just about breaking records, it's about building a timeline, a continuous chain of evidence connecting the universe's infancy to its present complexity. Every extreme galaxy adds a piece to the puzzle of how cosmic structure formed, how black holes emerged, and how light reclaimed the darkness of the early cosmos. Gravitational lensing as a cosmic telescope. There is no need for a bigger screen or a new satellite if you want to see farther than your telescope can. There are times when the universe itself acts as a magnifying glass. Gravitational lensing is a natural event that Einstein's theory of general relativity predicted. It is now one of the most powerful tools scientists use to study the world far away. At its core, lensing happens when big things like galaxies and clusters bend space-time, changing the way light from farther away sources travels. Light doesn't move in a straight line. Instead, it curves around the mass and comes to us through binoculars in different, often bigger shapes. There are two main kinds of lensing: strong lensing and weak lensing. Strong lensing occurs when the alignment between a distant source, a massive foreground object, and the observer is just right. The result can be dramatic: multiple images of the same galaxy, stretched arcs of light, or even the famous Einstein ring, where the source appears as a complete circle around the lensing mass. These features don't just look spectacular. They allow astronomers to study galaxies that would otherwise be invisible, magnified many times over by nature's own optics. Weak lensing, by contrast, is subtler. Instead of producing obvious arcs or multiple images, it creates small distortions in the shapes of background galaxies. By analyzing these distortions statistically across millions of galaxies, cosmologists can map the distribution of dark matter, which is otherwise invisible. Since dark matter makes up about 85% of the matter in the universe, weak lensing is a cornerstone of modern efforts to understand how cosmic structure grows and evolves. The usefulness of gravitational lensing goes beyond magnification. It acts as a kind of cosmic tomography, revealing both the properties of the background source and the mass of the lensing object itself. For example, clusters of galaxies that act as strong lenses allow researchers to weigh them with exquisite precision, mapping how dark matter is distributed within them. These maps are critical for testing theories of dark matter and for comparing observations to simulations of cosmic structure. Lensing has already pushed our view of the universe to astonishing depths. Some of the most distant galaxy candidates identified by the James Webb Space Telescope were spotted thanks to cluster lensing. Without magnification from clusters like Able 2744, nicknamed Pandora's cluster, these faint smudges of light would have been beyond JWST's reach. The magnification doesn't just make the galaxies brighter, it can also stretch their images enough to reveal structural details, giving us rare glimpses of the building blocks of the first galaxies. On top of magnifying galaxies, lensing also amplifies explosive cosmic events. Supernovae that would normally be too faint or distant to detect can suddenly appear in lensed fields, sometimes even producing multiple images of the same explosion that arrive at different times due to differences in light paths. These time-delay supernovae provide a direct way to measure the Hubble constant, since the delays are sensitive to the rate of cosmic expansion. In this way, lensing doesn't just let us see farther, it gives us new tools to measure fundamental parameters of the universe. Finding quasars that are split into multiple pictures is one of the most impressive examples of lensing. Some quasars, which are driven by supermassive black holes billions of light years away, look like they have 2, 3, or even 4 copies in the sky. Each one goes around the lensing mass in a slightly different way. Einstein's statements are not only proven true by these events, they also help us understand the structure of lensing galaxies and the distances between galaxies. There's also a frontier of lensing that's still developing: microlensing. This occurs when individual stars or compact objects within a galaxy pass in front of background stars, causing temporary brightening. While often used to search for exoplanets in our own galaxy, microlensing at cosmological distances can reveal the population of faint stars, black holes, and even rogue planets in other galaxies. It's an emerging field, but one that demonstrates how versatile lensing can be as a probe of both the near and far universe. Gravitational lensing is also a crucial cross-check for dark energy studies. By measuring how structures grow and how light bends across billions of years, lensing surveys provide an independent way to constrain the nature of dark energy, complementing supernova and cosmic microwave background measurements. Projects like the Vera C. Rubin Observatory's LSST and the Euclid mission are designed specifically to take advantage of weak lensing signals on a grand scale, mapping billions of galaxies to trace the invisible scaffolding of the cosmos. Of course, lensing can only do so much. Strong lensing isn't used very often because it needs to be aligned perfectly, which can affect pictures in ways that make them harder to understand. But the rewards are much greater than the problems. Nature helps binoculars see things that they can't, because it bends and boosts light from galaxies that would otherwise be hidden by time. Proto-galaxies in the first billion years. We don't see the big spirals and big ellipticals that are common in the sky today when we look very far back into the early universe. We see instead their poor beginnings, proto-galaxies, which are the clumpy, disordered galaxies that came before them. These faint, wavy structures appeared in the billion years following the Big Bang, when gas and dark matter started to be pulled together by gravity to form the building blocks of bigger galaxies. When you study them, it's like opening a time capsule that holds galaxies in the middle of becoming something they will become. Proto-galaxies were born in the dark ages that followed recombination. For hundreds of millions of years after the cosmic microwave background was released, the universe contained mostly neutral hydrogen and helium, with small density fluctuations imprinted by inflation. These fluctuations acted as gravitational wells, where dark matter clumped and began to draw in baryonic gas. Over time, these overdense regions collapsed, igniting the first stars and laying the foundation for proto-galactic clouds. Unlike modern galaxies, proto-galaxies were small and irregular. They often contained only a few million to a few hundred million stars, far fewer than the billions found in the Milky Way. Their shapes were chaotic, with loose clumps of gas and scattered clusters rather than well-defined disks. Collisions and mergers were common, since the young universe was denser and galaxies lay closer together. Each merger added to the process of building larger structures, feeding the growth of more massive systems over cosmic time. The first stars within proto-galaxies were probably the mysterious population 3 stars, massive metal-free objects formed from pristine hydrogen and helium. These stars lived short, violent lives, exploding as supernovae that enriched their surroundings with heavier elements. That enrichment was critical because it allowed later generations of stars to form planets, dust, and complex chemistry. Proto-galaxies were therefore crucibles, not just of structure, but of the ingredients needed for everything we recognize as cosmic complexity. Primordial galaxies are very hard to search for. They are small, faint, and often hidden by larger things in the background or center. They were more theory than practice for many years. Things have changed since the James Webb Space Telescope arrived, though. With JWST's infrared vision, scientists can see galaxies as they were just a few 100 million years after the Big Bang, at redshifts of Z(10 to 13. The things that JWST sees, which are mostly just smudges of light, are probably early galaxies that were caught in the process of coming together. Some of these proto-galaxies already show surprising maturity. JWST has revealed candidates with well-developed star-forming regions, and in some cases, hints of rotating structures resembling primitive disks. That's a puzzle, because many models predicted a slower buildup of ordered systems. The implication is that galaxy formation in the early universe may have been faster and more efficient than expected, possibly aided by strong flows of cold gas feeding star formation. The part they play in the epoch of reionization is another important thing about proto-galaxies. As proto-galaxies turned into stars, they released huge amounts of ultraviolet light that slowly charged the hydrogen gas around them, making the universe clear again. Reionization was probably caused by small galaxies, more than by rare quasars or big galaxies. This is because there are so many of them. Astronomers can get a better idea of when reionization happened and how long it lasted by looking at how many of them there are and how bright they are. Proto-galaxies also help us understand the growth of black holes. Many harbor the seeds of what would become supermassive black holes, perhaps formed from the collapse of the earliest massive stars or direct collapse gas clouds. The presence of luminous quasars less than 1 billion years after the Big Bang suggests that these seeds must have grown extremely rapidly. Proto-galaxies were the nurseries where this runaway growth began, linking star formation to black hole evolution in a tight feedback loop. Computer simulations, such as those from the Illustris and Fire projects, attempt to recreate proto-galaxy formation. These models show chaotic, turbulent systems, constantly fed by streams of gas from the cosmic web and constantly reshaped by mergers. They also show how stellar winds and supernova explosions regulated star formation, preventing proto-galaxies from burning through their gas too quickly. By comparing these simulations with JWST's new observations, astronomers are closing the gap between theory and reality, testing the physics of early star and galaxy formation in unprecedented detail. There are still a lot of questions. How common were proto-galaxies at the same time compared to galaxies that were already more developed? Did most of them make it to become parts of current galaxies? Or did many of them get ripped apart in violent mergers? How many of their stars were in population 3? And how fast did metal spread? Scientists are trying to figure out the stories behind some of the most big observational efforts of our time by trying to solve these puzzles. Quasar light from the edge. In the very beginning of the universe, long before galaxies formed beautiful spirals or huge ellipticals, some areas were very bright. These were quasars, which are very bright stars driven by supermassive black holes that eat matter very quickly. At the edge of what can be seen in the universe, quasars are so bright that they can be seen from more than 13 billion light-years away, brighter than their home galaxies. It's like shining a flashlight into the start of the universe to study them. They light up not only themselves, but also the space between galaxies that they pass through. A quasar works through a simple but extreme mechanism. At its heart sits a black hole with millions or even billions of solar masses. As gas spirals inward, it forms a superheated accretion disk, glowing in ultraviolet, X-ray, and optical light. The process is so efficient that quasars can radiate up to 1,000 times more energy than the Milky Way, despite their compact size. It's this incredible luminosity that makes them detectable even when they existed just a few 100 million years after the Big Bang. Some quasars lie at incredible distances, with redshifts greater than 7, meaning they formed less than 800 million years after the Big Bang. One example, Ulysses J 1120 plus 0641, discovered in 2011, hosts a black hole about 2 billion times the mass of the Sun and sits at a redshift of 7.1. More recently, the quasar J03131806 at a redshift of 7.6 stunned astronomers with a black hole already 1.6 billion times the Sun's mass. That existed when the universe was just 670 million years old. Discoveries like these raise a huge question. How did black holes grow so massive so quickly? Did they come from the collapse of enormous early stars, or from giant gas clouds collapsing directly under gravity? Quasars are valuable not just for their brightness, but also for the way their light interacts with the material between us and them. As photons from a quasar travel across billions of light-years, they pass through intergalactic hydrogen clouds. These clouds absorb specific wavelengths, creating a forest of absorption lines in the quasar's spectrum, the Lyman-alpha forest. By studying these patterns, astronomers can map the distribution of matter in the early universe and trace the timeline of the epoch of reionization. In fact, quasars have been instrumental in showing that by redshift 6, much of the hydrogen in the universe was already ionized. Quasars are also like lights in the universe for chemical development. The absorption lines in their spectra show that carbon, oxygen, and iron are present in the intergalactic medium. This shows how quickly heavy elements spread after the first star's burst. The fact that these metals show up so early is another sign that stars were being born and dying very quickly in the first few 100 million years. Among the strangest things about early quasars is how quickly their black holes grow. According to standard models, it should take billions of years for black holes to get to the mass of billions of suns. Still, they are huge now, less than 1 billion years after the Big Bang. To figure this out, scientists are looking into things like direct collapse black holes, which are situations in which huge clouds of gas don't form stars, but instead fall apart into black holes tens of thousands of times the mass of the Sun. Then, these seed black holes could eat quickly and join together to form the huge quasars we see today. Quasars also play a destructive yet creative role in galaxy evolution. The radiation and winds they produce can blow gas out of their host galaxies, suppressing star formation in some regions while compressing gas in others. This process, called AGN feedback, is thought to be critical in shaping the galaxies we see today. Even at the edge of the observable universe, quasars were already influencing their environments, sculpting the cosmic landscape around them. Detecting these quasars is no small feat. They are rare, and the farther back we look, the fewer there are to find. Wide-field surveys like the Sloan Digital Sky Survey and Pan-STARRS have identified many, but the James Webb Space Telescope is now poised to extend the search further. With its sensitivity to faint infrared light, JWST may uncover quasars at redshifts above 10, pushing our view even closer to the moment when the first black holes lit up. Cosmologists find quasars very interesting because they are not just memories from the past, they are also signs. We have to rethink how fast the universe is changing every time we find a new one at very high redshift. If supermassive black holes were around this early, galaxies, stars, and gas must have been forming even faster than we thought. So quasars are not strange things. They are important pieces of information that change the way we think about how the universe grew up. The Epoch of Reionization. The Epoch of Reionization can be thought of as the moment when the universe became truly clear. The cosmic microwave background is the moment when it first became see-through. The first stars and galaxies formed between 400 million and 1 billion years after the Big Bang. They emitted ultraviolet light that stole electrons from neutral hydrogen atoms. The universe went from being a cloudy fog to a clear space where light could easily move. This process, called reionization, made it possible for the structures we see in space today. To understand why this was important, visualize the universe before it became ionized. After recombination, hydrogen atoms were made, and the universe went through what people call the Dark Ages. Since there were no stars or galaxies, there were no bright sources of light in space. It was all neutral hydrogen. In theory, the universe was clear, but in fact, neutral hydrogen absorbed ultraviolet light, which made it hard for light from the first things to move far. As soon as the first bright objects like stars, proto-galaxies, and quasars were born, their energy started to tear electrons off of hydrogen atoms, which slowly cleared the fog. The drivers of reionization are still debated, but evidence points strongly to the countless small galaxies that filled the early universe. Each one produced relatively little light, but collectively they may have dominated the reionization process. Quasars also contributed, but they were rarer and probably too few in number to carry the full load. The efficiency of these galaxies depended on how many of their photons escaped into intergalactic space, a parameter astronomers call the escape fraction. Determining this value is one of the keys to understanding how quickly reionization unfolded. The epoch of reionization is studied through its impact on distant light sources. One of the most important tools is the Lyman-alpha forest, the series of absorption lines in quasar spectra caused by intervening hydrogen clouds. At redshifts greater than 6, many quasars show a Gunn-Peterson trough, a near-complete absorption of light bluewood of the Lyman-alpha line. This indicates that large amounts of neutral hydrogen still existed, providing a direct window into the timing of reionization. By redshift 6, these troughs largely disappear, showing that the universe was mostly ionized by then. Another promising tool is the 21 centimeter line of neutral hydrogen. This radio signal, produced by the spin-flip transition of hydrogen atoms, offers a way to map the distribution of hydrogen before and during reionization. Large radio observatories like LOFAR and the upcoming Square Kilometre Array are working to detect these signals, which would provide a three-dimensional view of how ionized bubbles grew and merged. Such maps could show reionization in action, revealing the patchy, uneven process by which the universe became transparent. Reionization was not uniform. Instead, it likely occurred in patches, with the first galaxies carving out ionized bubbles around themselves. These bubbles expanded, merged, and eventually percolated through the cosmos until little neutral hydrogen remained. Simulations show a universe riddled with these growing cavities, shaped both by the luminosity of galaxies and the density of surrounding matter. Observations of early galaxies with the James Webb Space Telescope are beginning to confirm this picture, identifying regions where galaxies are already surrounded by ionized gas while others remain opaque. The end of the epoch of reionization marks a fundamental transition. Before it, the cosmic web of gas was opaque to much of the light we use to study galaxies. After it, light could travel far more freely, enabling the universe to become the vast, transparent expanse we see today. Without reionization, our view of the cosmos would remain forever limited, blocked by the neutral hydrogen that once filled every corner of space. Reionization is also a key part of how galaxies change over time. It sent out very strong radiation that heated the gas between galaxies, which made it harder for small galaxies to gather matter and make stars. This process might help us understand why there aren't as many dwarf galaxies as models say there should be. It was both a phase that let light move and one that stopped many small buildings from growing. In spite of growth, there are still big questions. How did galaxies, black holes, and quasars split up the work of reionizing the universe? How long did reionization take? In a few 100 million years, was it over quickly? What do the oldest galaxies that JWST is finding, some of which look surprisingly old, tell us about how reionization happened? Every new finding changes how we think about this very important time. Cosmic dawn. The first stars. Population 3. The first stars were called Population 3 stars. They were there before galaxies and quasars, which were like cosmic lights. When these things formed, about 100 to 200 million years after the Big Bang, they marked the real beginning of the universe. They were different from stars we see today because they were only hydrogen and helium and not any stronger elements, which scientists call metals. Because their parts were so pure, they had special qualities. They were probably much heavier, hotter, and died much faster than any stars in our universe today. The absence of heavier elements is crucial here. In today's galaxies, metals like carbon, oxygen, and iron help cool collapsing gas clouds, allowing them to fragment into many small stars. In the early universe, those metals didn't exist yet. They had to be created later inside stars. Without efficient cooling, gas clouds collapsed into far larger chunks, producing giant stars that could weigh tens to hundreds of solar masses, perhaps even up to 1,000. These behemoths burned bright and hot, with surface temperatures exceeding 50,000 Kelvin, flooding their surroundings with ultraviolet radiation. Their lifespans were brief, often just a few million years. But in that time, they accomplished two crucial tasks. First, they helped drive the epoch of reionization by pumping out radiation that ionized hydrogen gas. Second, and perhaps more importantly, they created the first heavy elements through nuclear fusion in their cores. When they died, either through supernova explosions or direct collapse into black holes, they seeded the cosmos with the carbon, oxygen, and iron needed for later generations of stars, planets, and eventually life. In that sense, Population 3 stars were the universe's first alchemists, forging the building blocks of complexity out of pure hydrogen and helium. Today, one of the hardest things in astronomy is finding these stars directly. As of now, no Population 3 star has been seen by itself. This is because they lived and went so quickly and were so far away. Astronomers look for other kinds of proof instead. For instance, stars in our galaxy that have an extremely low metallicity, so-called fossil stars from a long time ago, may have the chemical signs of early enrichment from Population 3 supernovae. Also, galaxies with a very high redshift might have spectral signs that point to the presence of big stars that don't contain any metals. For example, they might have helium emission lines that are unusually strong or light that doesn't contain any stronger elements. The James Webb Space Telescope is a game changer in this search. With its infrared sensitivity, JWST can observe galaxies in the first few 100 million years of cosmic history, the very window when Population 3 stars should have existed. Some of its early results already show galaxies that are surprisingly bright for their age, hinting that massive stars, perhaps even population 3 stars, could have contributed to their light. If confirmed, this would be the first indirect glimpse of the cosmic dawn. Theoretical models and simulations add further intrigue. They predict that population 3 stars formed in small mini-halos of dark matter, weighing only about 1 million solar masses. These mini-halos collected gas from the surrounding universe, and once enough accumulated, a single massive star could ignite at the center. Over time, these halos merged, combining their stellar populations and beginning the process of galaxy formation. In some scenarios, the collapse of the largest population 3 stars may have also seeded the first black holes, the precursors to the supermassive black holes we now see in quasars. The violent deaths of these stars left distinctive signatures. Some may have exploded as pair instability supernovae, an extreme type of explosion that occurs when gamma rays in the star's core create electron-positron pairs, destabilizing the star and causing it to blow itself completely apart. These explosions are incredibly energetic and leave behind no remnant, scattering heavy elements into space. Detecting their chemical fingerprints in later generations of stars could provide direct proof that population 3 stars once lived. In addition to adding more chemicals to the universe, population 3 stars are very important for figuring out how fast it all became complicated. The reionization process may have been faster and more effective if they formed earlier or in larger numbers than models suggest. Galaxies and quasars would have done more of the work if they were less common. In any case, figuring out what role they played is important for putting together a history of the first billion years of the universe. Stars in population 3 are often the most mysterious parts of the story of the universe. We know they had to be there because the heavy elements that make up planets, DNA, and even our bodies would not have formed without them. Still, we've never seen them in person. Chemical fingerprints and models give us hints that they might still be out there, but we haven't found them yet. Gamma-ray bursts as distance markers. Gamma-ray bursts, GRBs, are very powerful events in the universe. They are short but stunning flashes of high-energy radiation that can light up whole galaxies. They explode without warning, and for short periods of time, usually just seconds to minutes. But in that 1 second, they give off more energy than the sun will give off in its whole life. GRBs are so bright that they can be seen from billions of light years away. This makes them very useful for measuring distances at the farthest edge of the universe that we can see. There are 2 main types of GRBs, classified by their duration. Short GRBs, lasting less than 2 seconds, are believed to result from mergers of compact objects such as neutron star pairs or neutron stars colliding with black holes. These cataclysmic events produce a burst of gamma rays, often followed by a faint afterglow in X-rays or optical light. Long GRBs, on the other hand, last longer than 2 seconds and are usually associated with the collapse of massive stars into black holes. These are sometimes accompanied by a hypernova, a particularly energetic type of supernova. Long GRBs are especially important for probing the early universe, since they are tied to star formation and the deaths of the first massive stars. The light of GRBs is what makes them useful for finding things far away. Today's telescopes can make even very faint galaxies look like they can't be seen, but a GRB inside one of them can shine so brightly that it can be seen from anywhere in the universe. In 2009, GRB 090423 was found to have come from a galaxy with a redshift of about 8.2. This was only 630 million years after the Big Bang. More recently, GRB 090429b may have been at Z less than 9.4, which would put it about 500 million years before the beginning of time. Astronomers can study times that would be impossible to reach otherwise thanks to these bursts, which act like cosmic beacons flashing from the edge of time. What makes GRBs particularly powerful tools is that their afterglows carry detailed information. As the blast wave plows into surrounding gas, it produces emission across the spectrum, from X-rays to radio waves. By studying this afterglow, astronomers can measure the redshift of the host galaxy and analyze the composition of intergalactic gas along the line of sight. GRBs, therefore, don't just tell us how far away they are. They also sample the intervening universe, acting as probes of reionization, chemical enrichment, and the structure of early galaxies. Scientists are looking into ways to use GRBs as standardizable candles, like how Type Ia supernovae are used to find out how far away things are in the universe. Even though GRB's light changes more, there are links between things like the burst's peak energy and its total energy output that suggest they could be measured. This method could be improved so that GRBs can reach farther into the universe than supernovae can. They could go into the early times when galaxies are faint and data is scarce. The connection between GRBs and the first stars adds another layer of significance. Some long GRBs may originate from population 3 stars, whose collapses would produce uniquely energetic and luminous bursts. Detecting such an event would provide the first direct observational evidence of these elusive first stars. In this way, GRBs could act as both markers of distance and signposts of cosmic dawn itself. Of course, GRBs can only do so much. Because they are so rare, they are hard to catch and need to be watched all the time. NASA's Swift and Fermi Gamma-ray Space Telescope are intended to find them in seconds and send signals to ground-based cameras so they can quickly follow up before the afterglow goes away. Even with this problem, GRBs are still one of the few ways to study the very beginning of the universe's past. Using GRBs to study the epoch of reionization is one of the most captivating concepts. Their afterglows can show how much neutral hydrogen is in the space between galaxies, which can show whether reionization was happening all at once or in patches at different times. GRBs happen in more common galaxies than quasars, which are very rare. They give us a wider and maybe more accurate picture of the early universe. The Sloan Great Wall and gigantic structures. When we picture the universe at its biggest, it's not just a big empty space with galaxies strewn around like garbage. Instead, galaxies form what is called the cosmic web, which is a complex structure made up of strands, clusters, and empty spaces. Some of the biggest structures ever found are in this web. The Sloan Great Wall, a huge collection of galaxies that spans more than 1.4 billion light-years, is one of the most well-known. Finding it reminded us that the structure of the world is much more complicated and linked than we thought. The Sloan Great Wall was identified in 2003 through data from the Sloan Digital Sky Survey, SDSS, one of the most ambitious mapping projects of the cosmos. Instead of looking at isolated galaxies, SDSS charted the three-dimensional distribution of hundreds of thousands of them, revealing large-scale patterns. Out of this data emerged the Sloan Great Wall, a sprawling wall of galaxies stitched together by gravity and cosmic history. Unlike individual clusters or superclusters, which contain thousands of galaxies, the Great Wall is a megastructure, a cosmic continent of sorts, stretching far across the sky. To grasp its scale, compare it to our own neighborhood. The local group, which contains the Milky Way and Andromeda, spans a few million light-years. Even our home supercluster, Laniakea, covers about 500 million light-years. The Sloan Great Wall is nearly 3 times larger than that, dwarfing structures we once thought were the upper limit of cosmic organization. Such walls challenge our sense of scale and force us to rethink how structure forms in a universe governed by dark matter and dark energy. The Great Wall is not the only one like it. The CFA2 Great Wall, an object about 500 million light-years across, was found in the 1980s and was shown in earlier studies. Since then, other huge walls have been found, such as the Hercules-Corona Borealis Great Wall, which may be up to 10 billion light-years long, though its reality is still up for question. These findings bring up a theme that keeps coming up. The universe naturally arranges itself into patterns that are incredibly big, with walls and threads surrounding huge holes. How do such structures form? The answer lies in the physics of gravitational clustering. After the Big Bang, the universe was nearly uniform, with only tiny density fluctuations. Over billions of years, gravity amplified those fluctuations. Dark matter, which interacts only through gravity, served as the skeleton of this process. Baryonic matter, ordinary gas, followed the gravitational pull of dark matter, condensing into filaments and eventually galaxies. The Great Walls are the result of this process on the largest scales, regions where filaments of galaxies intersect and merge, forming vast sheets. The cosmological principle says that the universe is flat and uniform on the biggest sizes. One notable effect of buildings like the Sloan Great Wall is how they relate to this idea. That is, the universe should look pretty much the same everywhere if you zoom out far enough. But when scientists find walls that are more than 1 billion light-years long, it makes you wonder how big things have to be before the universe really evens out. That limit is almost reached by the Sloan Great Wall. If there are even bigger walls, they might make our models of the universe less stable. The Sloan Great Wall is also used as a place to study how galaxies change over time. It is made up of groups and filaments that are full of galaxies in different stages of growth. There are a lot of galaxies that are still making stars in some areas, but elliptical, huge galaxies that have used up all their gas rule other areas. According to scientists, the environment affects galaxy growth, star formation, and black hole activity. They can figure this out by comparing galaxies in the wall to those in less dense environments. In addition, these massive walls help refine measurements of baryon acoustic oscillations, BAOs, the sound waves imprinted in the early universe's plasma that left subtle ripples in galaxy distributions. The Sloan Digital Sky Survey has been instrumental in detecting BAOs, and the presence of large structures like the Great Wall provides both a challenge and an opportunity. Are such walls statistical outliers, or are they natural features predicted by our models of structure formation? Comparing them to simulations of the cosmic web helps answer that. The Hercules-Corona Borealis Great Wall. For those of us who thought the Sloan Great Wall was big, the finding of the Hercules-Corona Borealis Great Wall, HCBW, in 2013 really shook us up. This huge structure, which is said to cover almost 10 billion light-years, is not only bigger than any other structure we know of, but it also seems to go against everything we know about the universe. If it turns out to be true, it would be bigger than any galaxy cluster, filament, or wall we've ever seen. This brings up the disturbing question: can the universe really be uniform at the biggest scales? The HCBGW wasn't discovered through galaxy surveys like the Sloan Great Wall. Instead, it emerged from the study of gamma-ray bursts, GRBs. Because GRBs are so bright, they can be detected at immense distances, serving as tracers of where massive stars once lived and died. When researchers analyzed the distribution of GRBs in the sky, they noticed a startling pattern. Dozens of them seemed to cluster in a broad swath of space stretching across the constellations Hercules and Corona Borealis. The clustering suggested the presence of an enormous structure, far larger than anything previously seen. To appreciate its scale, consider that the observable universe itself has a radius of about 46 billion light-years. The Hercules-Corona Borealis Great Wall, if real, spans nearly a quarter of that radius. It would be several times larger than the Sloan Great Wall, and perhaps the largest coherent structure in the observable universe. The problem? Standard cosmology, built on the cosmological principle, assumes that on scales above about 1.2 billion light-years, the universe should appear uniform. Structures much larger than that are not just unexpected, they're supposed to be statistically impossible. This is why the discovery sparked intense debate. Some astronomers argue that the clustering of GRBs may be a statistical fluke, a byproduct of the limited sample size and uneven observational coverage. GRBs are rare and randomly distributed in time, which makes them less reliable as precise traces of cosmic structure compared to galaxies or quasars. Others suggest that while the structure appears enormous in projection on the sky, it may not be a single coherent feature, but rather a chance alignment of smaller, unconnected regions along our line of sight. Still, we can't rule out the chance that the HCBGW is real. We would have to look again at the size at which cosmic uniformity starts to hold true, if it is true. It's possible that the universe isn't as smooth on a large scale as we think, or that there were physical processes in the early universe that caused even bigger changes than what inflationary theory suggested. No matter what, it would mean that our existing models of the universe are not full. What would such a colossal structure even look like up close? If the Sloan Great Wall is a continent of galaxies, the Hercules-Corona Borealis Great Wall would be an entire supercontinent, made of countless filaments, clusters, and voids woven together. Within it would be hundreds of thousands of galaxies, clusters as massive as any we've studied, and likely complex networks of dark matter scaffolding the entire thing. Its sheer size would mean that light takes billions of years just to traverse it, longer than complex life has existed on Earth. Surveys in the future might help settle the argument. The Euclid Project and the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will make maps of where galaxies and quasars are located with a level of detail that has never been seen before. This will help us figure out if objects on this scale really do exist. If the GRB grouping is proven by separate tracers, the Hercules-Corona Borealis Great Wall will be a strange event in the universe, a reminder of something we don't fully understand about how structures are built yet. Cosmic voids at the edge. Galaxy walls and filaments show how crowded the cosmic web is, but the empty places between them show another interesting side of the universe: cosmic voids. In these very large areas, galaxies are not common, matter density is very low, and nothingness is the main thing. Voids are not just empty spaces between structures. They have a big impact on how the universe changes over time, on how galaxies grow at their edges, and they can even be used to test the accuracy of cosmic models. At the edge of the universe that can be seen, voids are very important for understanding why reionization isn't uniform and matter is spread out unevenly at the biggest scales. A cosmic void is not completely empty. Instead, it contains a thin smattering of galaxies, diffuse gas, and of course dark matter, but at densities often less than 10% of the cosmic average. In surveys of the local universe, voids can stretch across tens to hundreds of millions of light years. At greater distances, when the universe was younger and less structured, voids were smaller but still influential, acting as low-density bubbles around which the cosmic web assembled. Voids are detected by mapping galaxy surveys and identifying regions where galaxies are conspicuously absent. For example, the Bootes void, one of the largest nearby examples, spans about 330 million light-years and contains only a few dozen galaxies, where thousands might be expected. At the edge of the observable universe, voids are harder to pinpoint because galaxies are faint and sparse, but their imprint shows up in other ways, such as in the cosmic microwave background, CMB, and quasar absorption spectra. The CMB cold spot is one of the most interesting signs of a big empty space far away. This surprisingly cool area in the microwave background is in the southern hemisphere of the sky. This could be because there is a huge empty space in front of us. The combined Sachs-Wolfe effect means that photons lose energy as they pass through areas that are not densely packed. This could leave behind colder spots on the CMB map. People are still arguing about whether the cold spot is just a statistical oddity or proof of a huge empty space. However, it does show how empty spaces can leave a trace in the universe's oldest light. Voids also affect how galaxies evolve at their boundaries. In denser filaments and clusters, galaxies interact frequently, merging and triggering bursts of star formation. In contrast, galaxies within or near voids tend to evolve in isolation, with slower star formation and fewer interactions. By studying galaxies on the edges of voids, astronomers can test how the environment influences growth and diversity. At the universe's far edges, such observations are especially valuable, since they reveal the earliest differences between dense and underdense regions. From a theoretical perspective, voids are sensitive probes of dark energy and cosmic expansion. Because their evolution is strongly influenced by the overall expansion rate, their size and growth pattern can test cosmological models. For example, a faster expansion rate tends to make voids grow larger and emptier, while modifications to gravity would leave different signatures in their structure. Surveys, such as the Sloan Digital Sky Survey and future missions like Euclid, aim to use void statistics as cosmological rulers, complementing more traditional probes like supernovae and Baryon acoustic oscillations. Voids are also critical in understanding large-scale homogeneity. The cosmological principle assumes the universe is uniform at the largest scales, but the existence of immense voids pushes against that assumption. Just as the Sloan Great Wall challenges our sense of maximum size for cosmic structures, giant voids challenge our sense of minimum density. If voids much larger than expected are confirmed near the observational horizon, it could hint at new physics beyond the standard cosmological model. During the epoch of reionization, when redshifts were high, gaps were very important. Less crowded areas reactivate more slowly, leaving behind neutral hydrogen for longer than denser areas. This uneven reionization means that the universe didn't turn clear all at once, but in a messy way that depended on where galaxies formed and where they didn't. As a result, voids are not just inactive observers. They are actively involved in the events of the cosmic dawn. Detecting distant voids requires creative methods. One approach is to use the Lyman-alpha forest in quasar spectra, where gaps in absorption lines correspond to underdense regions. Another is to analyze the distribution of faint galaxies with JWST and future radio surveys, mapping out where the early cosmic web was thick and where it was nearly absent. Together, these tools can reveal the hidden geography of the young universe, filling in the blank spaces on our maps. The cold spot in the CMB. The cosmic microwave background, CMB, is the weak afterglow of the Big Bang. It has uneven patterns that have puzzled cosmologists for almost 20 years. This is where the cold spot is. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, was the first to find this area, and the European Space Agency's Planck satellite later confirmed it. It looks a lot cooler than the rest of the sky and covers almost 5 degrees. It might look like just another random change in the CMB at first glance, but its size and depth have brought up questions that go beyond simple statistical chance. The CMB itself is a remarkably uniform bath of radiation, at a temperature of about 2.7 Kelvin, with fluctuations of only a few parts in 100,000. These tiny variations correspond to density differences in the early universe that seeded the growth of galaxies and clusters. Most of the spots we see in the CMB are exactly what cosmologists expect from inflationary theory and the physics of recombination. The cold spot, however, is unusual. It is larger and colder than typical fluctuations, and some analyses suggest the odds of such a feature arising purely by chance are very low, perhaps less than 2%. One possible explanation is that the cold spot is the result of a gigantic cosmic void along our line of sight. As photons from the CMB pass through underdense regions, they can lose energy due to the integrated Sachs-Wolfe effect, arriving slightly cooler than expected. If a massive void lies between us and the CMB, it could imprint a cold region in the background map. Indeed, surveys of galaxies in that direction have identified a large void, sometimes called the Eridanus supervoid, which could contribute to the cold spot. However, whether the void is large and deep enough to explain the entire anomaly remains debated. Another possibility is that the cold spot is simply a statistical fluke. After all, when analyzing data across the entire sky, rare features are bound to show up. Just because the cold spot looks unusual doesn't mean it breaks the rules. It might just be the tail end of the expected distribution of fluctuations. This explanation is favored by many cosmologists, who argue that extraordinary claims require extraordinary evidence, and the cold spot doesn't yet rise to the level of rewriting cosmology. People are still curious in the cold spot because it might be a sign of something new in physics. Some ideas that are just guesses say it might be the mark of a bubble universe or something strange that happened during inflation. Even though these ideas are interesting, they are still very much just guesses. Most experts prefer more logical answers, such as voids or random chance. Still, the fact that the strange thing keeps happening keeps the conversation going, which is why the cold spot is still one of the most talked about parts of the CMB. The cold spot also illustrates the power of modern cosmological surveys. Without missions like WMAP and Planck, we wouldn't even know it existed. Planck, in particular, provided high-resolution maps that confirmed the cold spot's presence, ruling out earlier concerns that it was an artifact of instrumentation or data processing. What's left is a real feature on the sky, one that demands explanation, whether mundane or profound. The cold spot is both bad and good news for astronomers. At first glance, it might just be a random change that serves as a warning that chance events can lead to strange results. On the other hand, if more research shows that normal models can't explain it, it might force us to rethink what we think we know about the early universe, inflation, or the structure of space on a big scale. Either way, the result is useful. Either we find cracks in our models where new physics could enter, or we show that our models are strong. Baryon acoustic oscillations as rulers. Before galaxies were made, the universe was full of photons, electrons, and protons that were very hot and thick. Pressure waves spread outward in that early soup like sound waves in the air. These waves, called baryon acoustic oscillations, BAOs, left marks that we can still see in the way galaxies are spread out billions of years later. The marks are weak but measurable. That's why BAOs are so useful. They give cosmologists a standard ruler, a set scale that lets them measure lengths across the universe with amazing accuracy. The origin of BAOs lies in the balance between gravity and radiation pressure. Gravity tried to pull matter together, while the intense radiation of the early universe pushed it apart. This tug-of-war created expanding sound waves in the plasma, radiating outward from initial density fluctuations. When the universe cooled enough for photons to decouple at recombination, around 380,000 years after the Big Bang, these waves froze in place. The result was a preferred scale in the clustering of matter. Galaxies today are slightly more likely to be separated by about 500 million light-years in comoving distance than by other scales. Detecting this subtle preference requires surveying millions of galaxies. The Sloan Digital Sky Survey, SDSS, and later surveys like the Baryon Oscillation Spectroscopic Survey, BOSS, measured the positions and redshifts of galaxies across vast volumes of space. The data revealed the faint but unmistakable BAO signal, a peak in the correlation function showing that galaxies are indeed distributed with this characteristic separation. It's a tiny effect, just a fraction of a percent enhancement, but with large enough samples, it stands out. Why does this matter so much? Because BAOs give cosmologists a ruler that doesn't change over time. By comparing the observed size of the BAO scale at different redshifts, astronomers can measure how the universe's expansion has changed over billions of years. This makes BAOs one of the most powerful probes of dark energy, the mysterious force driving cosmic acceleration. Alongside Type Ia supernovae and the cosmic microwave background, BAOs form a critical part of the cosmic distance ladder. BAOs also serve as a bridge between early universe physics and late-time structure. The same sound waves that left ripples in the cosmic microwave background left their fossilized mark in the galaxy distribution. By combining CMB measurements of those early oscillations with BAO measurements today, cosmologists can test whether the universe has evolved as expected. If the two signals didn't match, it would suggest something is missing in our understanding of cosmic history. Beyond galaxies, BAOs also appear in the Lyman-alpha forest, the absorption features seen in the spectra of distant quasars. This allows astronomers to push BAO measurements to even higher redshifts, probing closer to the epoch of reionization. Future surveys aim to detect BAOs using 21 centimeter hydrogen signals offering another window into the earlier structures. The more methods we have to measure BAOs, the more robust our cosmological conclusions become. Systematic mistakes don't affect BAOs very much, which makes them very strong. BAOs are marked by basic physics from the beginning of the universe, while supernovae can be changed by dust, metals, or errors in the measurement process. For that reason, they are clean, regular, and dependable. A kind of universal ruler we can depend on in both time and space. The BEO signal also gives us information about dark matter and the shape of space. One example is that the form of the BEO peak helps us figure out if the universe is flat, open, or closed. As expected from inflation, the most recent statistics show that it is surprisingly flat. Also, the way the BAO scale changes with redshift helps to check the Hubble constant on its own, which helps to see if there are any problems with the way different measures of the expansion rate of the universe are putting them together. Type Ia supernovae as standard candles. The idea that type Ia supernovae could be used as accurate distance marks, called standard candles, to map the expansion of the universe was one of the most important discoveries in the history of astronomy. Not only do these starbursts let us figure out how far away galaxies are, but they also shocked everyone in the late 1990s by showing that something called dark energy is speeding up the expansion of the universe. Type Ia supernovae occur in binary systems, where a white dwarf star orbits a companion. Over time, the white dwarf siphons material from its partner until it approaches the Chandrasekhar limit, about 1.4 solar masses. At this point, the pressure in the star's core can no longer resist gravity, leading to runaway nuclear fusion that ignites the entire star in a thermonuclear explosion. Because this critical mass is nearly the same for every white dwarf that reaches it, the resulting explosions have very similar peak luminosities. That uniformity makes them ideal for use as cosmic yardsticks. By comparing a type Ia supernova's intrinsic brightness to how bright it appears from Earth, astronomers can calculate its distance. Combined with its redshift, this provides a powerful way to measure the expansion rate of the universe across billions of light years. Unlike Cepheid variables, which work best for nearby galaxies, type Ia supernovae can be seen much farther out, sometimes more than 10 billion light-years away, making them indispensable for probing the distant cosmos. In the late 1990s, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, used type Ia supernovae to map the expansion history of the universe. They expected to find that expansion was slowing down under the pull of gravity. Instead, the data showed that distant supernovae were dimmer than predicted, meaning they were farther away than expected. The shocking conclusion: the universe's expansion is not slowing, but accelerating. This was the discovery of dark energy, a component of the cosmos that now accounts for roughly 70% of its total energy density. This is how type Ia supernovae can be used as standard candles with confidence. Scientists study the universe and use formulas like the Phillips relation to figure out things like how fast a supernova's light drops after it peaks and how bright it really is. This lets them fine-tune their distance predictions, which cuts the error down to a few percent. The Sloan Digital Sky Survey's supernova program and the Dark Energy Survey have looked at thousands of supernovae to make these tools better. Despite their power, type Ia supernovae aren't perfectly uniform. Some explosions are slightly brighter or dimmer than average, depending on details like the composition of the white dwarf, the nature of its companion, and the environment in which it resides. Dust in the host galaxy can also dim the light, complicating distance measurements. But with statistical corrections, these challenges can be managed, allowing type Ia supernovae to remain one of the most precise tools for cosmology. Today, type Ia supernovae are used in combination with other probes, like Baryon acoustic oscillations and the cosmic microwave background, to build a consistent picture of the universe's expansion history. Together, they allow cosmologists to constrain the properties of dark energy and test whether it behaves like a cosmological constant. as Einstein once suggested, or evolves over time. Supernovae also check the Hubble constant, which is the rate of growth at the moment. Astronomers like Adam Rees and his colleagues have measured a local value of the Hubble constant that seems to be different from the value derived from the CMB. They did this by fixing the distance scale with Cepheids and correcting it with supernovae. The so-called Hubble tension is still one of the biggest mysteries in modern astronomy. Type Ia supernovae are at the center of the argument. Type Ia supernovae are useful, but they are also amazing events in the universe. They put iron and other heavy elements into galaxies at the start, which affects how chemicals change and how planets form. The chemical table and life itself would look very different without them. In this way, their role in astronomy and their role in the past of the universe are linked, both as ways to measure distance and add to the story. Redshift drift. Most of the tools we use to study the universe are snapshots. For example, we use them to measure how far away galaxies are, how bright supernovae are, and how the cosmic microwave background looks when time stops. We could do something really cool, though, with one effect. Watch the growth of the world change in real time. Redshift drift, or the Sandage-Loeb test, is the name of this effect, after the scientists who first came up with it. The idea comes from a simple fact. The speed at which the world is expanding doesn't stay the same. It's moved more slowly in the past because of gravity, and faster again because of dark energy. It's still changing right now. Today, you can measure a galaxy's redshift, which is how much its light has been stretched by expanding. But if you look at the same galaxy again a few hundred or a few thousand years from now, its redshift will be a little different. This is because the rate of growth will have changed during that time. If we look at that tiny shift over millions of galaxies, we might be able to see cosmic acceleration happen right now. The predicted effect is incredibly small. For a galaxy at redshift Z tilde 4, the drift is only about a few centimeters per second per year in terms of velocity shift. That's far below what current instruments can detect. But with the next generation of high-precision spectrographs, such as those planned for the Extremely Large Telescope, ELT, astronomers hope to measure this drift over a timescale of 10-20 years. The technique would rely on observing the Lyman-alpha forest, the dense pattern of absorption lines in the spectra of distant quasars, which provides many fine features that can reveal tiny shifts. Why is this so important? Because redshift drift offers a direct model-independent test of cosmic expansion. Other methods like supernovae or Baryon acoustic oscillations rely on calibrations, assumptions, or indirect comparisons. Redshift drift, by contrast, is a pure measurement. Watch the same object's spectrum over time and see how it changes. If the universe is accelerating, the drift will be positive. If it were decelerating, the drift would look different. It's as close as we can get to putting a speedometer on the cosmos itself. The potential scientific payoff is huge. Detecting redshift drift would give us new leverage on dark energy, helping distinguish whether it behaves like a cosmological constant or something more exotic that evolves with time. It would also provide independent confirmation of the standard LCDM cosmological model, or reveal discrepancies that point toward new physics. Because the effect is tied directly to the Friedmann equations of general relativity, measuring it would test not just dark energy, but also our understanding of gravity on the largest scales. There are challenges, of course. The need for ultra-precise measurements over decades means this is a long-term experiment, requiring patience and technological advances. Instruments like HIAS on the ELT are being designed with this in mind, capable of the stability and sensitivity required to detect velocity shifts of just a few centimeters per second. While we may not see definitive results for several decades, the groundwork is being laid today. Another good thing about redshift drift is that it doesn't have as many systematic errors as other cosmological tools. It is not affected by dust, changes in the galaxy, or mistakes in the measurements because it only looks at how the spectral lines move relative to each other over time. It's a clean number because it's so easy to use, even though it's hard to understand. Spectral lines from the first atoms. There were no atoms in the world after the Big Bang because it was too hot and dense. It was full of free protons, electrons, and helium nuclei for the first few 100,000 years. But as the universe grew and cooled, something amazing happened. Electrons joined with nuclei to make the first neutral atoms, which were mostly hydrogen, with a small amount of helium. This process, called recombination, not only made the universe visible to light, creating the cosmic microwave background, but it also left behind a set of spectral lines that show how the universe was put together in the beginning. The most important of these lines comes from hydrogen, the simplest and most abundant element in the cosmos. When electrons settle into hydrogen atoms, they can absorb and emit photons at discrete wavelengths, the most famous being the Lyman series in the ultraviolet. These transitions shaped how the first atoms interacted with radiation, and their echoes can still be seen today in the spectra of distant quasars such as the Lyman-alpha forest. Each absorption line corresponds to a cloud of hydrogen along the line of sight, mapping out the distribution of matter across billions of light years. Helium also left its mark. Formed during Big Bang nucleosynthesis just minutes after the Big Bang, helium atoms produced distinct spectral lines when they captured electrons. Detecting these features in the early universe is more challenging than hydrogen, but they provide crucial confirmation that primordial nucleosynthesis happened exactly as predicted. By comparing the abundance of hydrogen and helium lines with theoretical models, astronomers can test the physics of the early universe with exquisite precision. These spectral lines are more than just chemical fingerprints, they are tools for cosmology. For instance, the strength and shape of hydrogen absorption lines give direct information about the temperature and density of the intergalactic medium at different epochs. By tracking how these properties evolved, we can reconstruct the timeline of cosmic cooling, reionization, and structure formation. They also serve as sensitive probes of the matter distribution, acting like a cosmic topographic map that reveals the clumpiness of gas at different scales. The look for basic constant variations is a very interesting way to use spectral lines. Atheists can check to see if constants like the fine structure constant or the electron-to-proton mass ratio have changed over cosmic time by comparing hydrogen lines seen billions of years ago to those recorded in labs today. So far, no clear change has been found, but the accuracy is getting better all the time, and even a small change would have huge effects on physics. Spectral lines from the first atoms are also tied to the 21 centimeter line, a radio signal emitted when the spin of a hydrogen atom's electron flips relative to its proton. This transition allows astronomers to probe neutral hydrogen across cosmic history even before galaxies and stars formed. Detecting 21 centimeter signals from the cosmic dark ages, before the first stars lit up, is one of the holy grails of modern astronomy. Arrays like LOFAR, HERA, and the upcoming Square Kilometre Array, SKA, are designed to capture this faint radiation, mapping hydrogen at redshifts far beyond what optical telescopes can reach. Together, these lines provide a consistent story. The early universe was simple, predictable, and dominated by hydrogen and helium. By studying their imprints, we test the most fundamental aspects of cosmology, from the success of Big Bang nucleosynthesis to the details of reionization. Every photon absorbed or emitted by hydrogen and helium in the early cosmos adds another thread to the tapestry of cosmic history. Still, there are problems. The lines we see now are much farther in the infrared and radio because the universe is expanding. To see them, you need high-tech tools that can cut through background noise like galaxies, dust, and our own Milky Way. Still, things are moving quickly forward. With JWST focusing on galaxies close to the time of reionization and radio telescopes searching for the 21 centimeter signal, we are now closer than ever to being able to directly trace the change from the first atoms to the first stars. The Lyman-alpha forest. A quasar is one of the brightest stars in the universe. When scientists point their telescopes at it, they don't just see a clean spectrum of light from the quasar itself. Instead, they see a tangle of absorption lines, which are points where the light is less bright in the ultraviolet range. This complex web of lines is known as the Lyman-alpha forest, and it is one of the best ways to learn about the world between galaxies. The forest originates from neutral hydrogen atoms scattered throughout intergalactic space. Each time light from a quasar passes through a cloud of hydrogen, some of it is absorbed at the wavelength corresponding to the Lyman-alpha transition, 121.6 nanometers in the rest frame. Because the universe is expanding, the absorption from each cloud is redshifted by a different amount, depending on the cloud's distance. The result is not a single line, but a whole forest of them, each marking a hydrogen cloud along the line of sight, stretching across billions of light years. What makes the Lyman-alpha forest so valuable is that it provides a three-dimensional map of matter distribution. Galaxies are bright and relatively rare, but hydrogen clouds are everywhere, tracing the underlying cosmic web of dark matter and gas. By analyzing the spacing and strength of absorption lines, astronomers can reconstruct how matter is distributed on both small and large scales. This makes the forest one of the best probes of the universe's structure between redshifts 2 and 6, a critical period when galaxies and quasars were rapidly forming. The forest also acts as a cosmic thermometer. The width of absorption lines reflects the temperature of the intergalactic medium, since hotter gas produces broader lines. By studying these line widths across different redshifts, astronomers can measure how the universe heated and cooled over time, especially during and after the epoch of reionization. For example, the forest shows that by redshift approximately 6, hydrogen was mostly ionized, marking the completion of reionization. It is also very important for the Lyman-alpha forest to measure the Baryon acoustic oscillation, BO signal at high redshift. The forest shows BO patterns in the intergalactic medium from earlier times, just like galaxy studies show them at lower redshifts. Baryon oscillation. Spectroscopic survey, BOSS projects, have used thousands of quasar spectra to find BOs in the forest. These measurements give us a better understanding of how the universe has grown over time. This has helped put more limits on dark energy and the way space curves. The forest also helps constrain the nature of dark matter. If dark matter were warm instead of cold, it would prevent the formation of small-scale structures, smoothing out the absorption lines. By comparing simulations of different dark matter models to the observed forest, astronomers can place limits on the properties of dark matter particles. Current data strongly favor cold dark matter, but the forest remains a sensitive probe for alternative theories. The huge amount of life in the Lyman-alpha forest is one of its intriguing features. There can be hundreds of absorption lines in a single quasar spectrum, and each one is connected to a different part of the intergalactic medium. As scientists look at many quasars from different angles, they can put these flat probes together to make a three-dimensional picture of the cosmic web. Surveys like DSI, Dark Energy Spectroscopic Instrument, are now using this method on tens of thousands of quasars, which is changing the forest into a big map of the universe. But the forest isn't just about mapping gas. It also reveals the chemical evolution of the universe. Alongside hydrogen absorption, some lines show traces of heavier elements like carbon, silicon, and oxygen. These metals were forged in early generations of stars and dispersed into intergalactic space by galactic winds and supernovae. Their presence in the forest shows how galaxies enriched the cosmos, spreading the seeds of future stars and planets far beyond their boundaries. Studying the Lyman-alpha forest requires both precision and patience. The absorption lines are faint and narrow, demanding high-resolution spectroscopy. Instruments like the Keck-Hires spectrograph and the Very Large Telescope's UVES have provided the most detailed spectra so far. But the next generation of observatories, including the Extremely Large Telescope, ELT, will push even further, allowing astronomers to sample the forest with unprecedented detail and extend it to earlier times. 21 centimeter cosmology. The Lyman-alpha line is often what we think of when we think about hydrogen's place in the universe, but the 21 centimeter line, a smaller but more interesting change, has become one of the best ways to look into the early universe. Astronomers can study eras that are normally unseen to regular telescopes thanks to this weak radio signal. It is made by neutral hydrogen atoms when the electron spins flip relative to their protons. We might even be able to map the universe during the cosmic dark ages, which is a time before the first stars and galaxies were formed. The 21 centimeter signal arises from what's called the hyperfine transition in hydrogen. Normally, the electron and proton spins align or anti-align, and when they flip states, the atom emits or absorbs a photon with a wavelength of 21 centimeters, frequency approximately 1.42 gigahertz. While this transition is rare for any given atom, the sheer abundance of hydrogen in the universe makes the combined effect significant. As the universe expands, this emission is redshifted, shifting into meter to decameter long wavelengths, depending on when it was produced. By measuring the frequency of 21 cm radiation, astronomers can determine the redshift of the hydrogen, effectively creating a time machine to track the state of the universe at different epochs. Exploring the cosmic dark ages, the time between recombination, about 380,000 years after the Big Bang, and the birth of the first stars, about 100–200 million years later, is one of the most interesting uses. At this time, the universe was made up of neutral hydrogen, but there were no bright things to light it up. While optical and infrared cameras can't directly look into this time period, the 21 cm signal makes it possible to map it out in 3 dimensions. Finding this signal would show how matter was spread out before galaxies were even thought of, giving us clues about how structures start to form. The 21 cm line is equally powerful for studying the epoch of reionization. As the first stars and galaxies formed, they ionized hydrogen in their surroundings, carving out bubbles of ionized gas in the neutral intergalactic medium. These bubbles expanded, overlapped, and eventually cleared the fog. By observing fluctuations in the 21 cm signal at different redshifts, astronomers can watch this process unfold, seeing when and how reionization happened, and which sources were most responsible. In this way, 21 cm cosmology promises to fill the gap between the cosmic microwave background and the first galaxies. Detecting the 21 cm signal, however, is extremely challenging. The emission is faint, and by the time it reaches Earth, it is buried under much stronger foreground noise from our galaxy and terrestrial interference. To isolate the cosmological signal, researchers must separate it from galactic synchrotron radiation and other contaminants with extreme precision. Instruments like LOFAR, Low Frequency Array, in Europe, MWA, Murchison Wide Field Array, in Australia, and HERA, Hydrogen Epoch of Reionization Array, in South Africa, are all working to detect this elusive radiation. The upcoming Square Kilometre Array, SKA, the largest radio telescope ever planned, will take this effort to the next level, offering the sensitivity to map 21 cm signals across vast cosmic volumes. In 2018, the EDGES experiment in Australia reported a tentative detection of a global 21 cm absorption signal at redshift approximately 17, corresponding to about 180 million years after the Big Bang. The signal appeared stronger than expected, suggesting that hydrogen was cooler than standard models predicted. If confirmed, this could point to new physics, such as interactions between dark matter and baryons. While follow-up experiments have yet to confirm the result, it illustrates the potential of 21 cm cosmology to not only map the universe, but also test fundamental physics. The 21 cm line is useful for studying more local structures. Radio observations of galaxies use the line to measure rotation curves, revealing the presence of dark matter halos. On larger scales, 21 cm intensity mapping can trace the distribution of hydrogen gas across billions of light-years, complementing optical galaxy surveys and providing an independent way to measure baryon acoustic oscillations. If it works, 21 cm cosmology could change the way we think about the beginning of the world. We could see the first structures form, follow the reionization process, and even test the physics of dark matter and dark energy in ways that can't be done any other way. It would turn the Dark Ages from a vague time period into a mapped, visible era. High-energy cosmic rays from distant sources. In the vastness of the world, not all messages come in the form of light. It takes some particles billions of years to get to Earth's atmosphere, where they hit it at almost the speed of light. Cosmic rays are the most powerful particles that have ever been seen in nature. Their origins are still a mystery, but their high speeds and long trips make them important tools for studying the faraway universe. They may also be the most dramatic reminders that the universe can send us signs in many forms. Cosmic rays are mostly protons and atomic nuclei, shot to incredible energies by powerful cosmic engines like supernova remnants, active galactic nuclei, and gamma-ray bursts. Most of the cosmic rays we detect on Earth are relatively low energy and come from within our own galaxy. But the ultra-high energy cosmic rays, or UHCRs, with energies above 10 to the 18th electron volts, are far rarer and much more mysterious. At the very top of the spectrum are particles with energies above 10 to the 20th electron volts, 100 million times more energetic than anything produced by the Large Hadron Collider. A single proton at that energy, in theory, could knock a golf ball across a course if you could somehow capture it intact. One of the biggest puzzles about UHCRs is how they can exist at all. At such extreme energies, they should interact with the cosmic microwave background, the faint bath of radiation left over from the Big Bang. Above about 5 times 10 to the 19th electron volts, protons colliding with those background photons should lose energy in a process called the Greisen-Zatsepin-Kuzmin cutoff, or GZK cutoff. This should limit their travel to no more than about 100 million light-years before they degrade. Yet detectors on Earth continue to catch particles that seem to exceed this limit, leaving astronomers wondering, where exactly are these extraordinary particles coming from? The sources of UHCRs remain uncertain. Some candidates include the jets of active galactic nuclei, AGN, where supermassive black holes spew out particles at relativistic speeds, gamma-ray bursts, whose powerful shocks could accelerate particles to ultra-high energies, and the shockwaves around massive clusters of galaxies. Pinpointing the sources is difficult, however, because cosmic rays are charged particles. As they travel across intergalactic space, they are deflected by magnetic fields, scrambling their arrival directions by the time they reach Earth. This makes them harder to trace back to their origins compared to neutral messengers like photons or neutrinos. To study these extreme particles, massive ground-based observatories have been built. The Pierre Auger Observatory in Argentina spans 3,000 square kilometers, using an array of detectors to measure the showers of secondary particles produced when cosmic rays strike the atmosphere. Similarly, the Telescope Array project in Utah monitors the sky for high-energy events. By analyzing the frequency, direction, and energy of incoming particles, these facilities aim to unravel the mystery of where UHCRs come from and how they achieve such extraordinary energies. Cosmic rays also carry information about the universe. Their spectrum and spread tell us about the structure of the universe on a big scale and how dense magnetic fields are between galaxies. In fact, UHCRs might be one of the only ways to find out how strong and how these mysterious magnetic fields are arranged. These fields affect how galaxies and clusters change over time. Fundamental physics is also put to the test because reactions at these energies look into realms that human-built accelerators can't reach. If changes from expectations are found, studying them might even lead to the discovery of new particles or forces. UHCRs are linked to multi-messenger astronomy, where observations of cosmic phenomena combine signals from photons, neutrinos, gravitational waves, and cosmic rays. For example, detecting both high-energy neutrinos and cosmic rays from the same source would be a breakthrough, directly tying extreme particle acceleration to specific astrophysical objects. While such coincidences are rare, efforts by observatories like IceCube in Antarctica and Auger are moving us closer to this goal. Neutrinos traveling across billions of years. Neutrinos are like the universe's whispers. Cosmic rays are its loud shots. Neutrinos are almost massless, chargeless particles that can move through the universe without being stopped, absorbed, or blocked. They are some of the most common particles in the world. Trillions of them pass through your body every second, but they don't interact with matter very often, making them very hard to find. Neutrinos, on the other hand, are very important for astronomy because they can bring us information from billions of years ago that hasn't changed at all. The story of cosmic neutrinos begins not long after the Big Bang. Within the first second of cosmic history, as the universe was still a hot plasma of particles and radiation, neutrinos decoupled from the rest of the matter. Since then, they have traveled freely through space, forming a background known as the cosmic neutrino background, CNB. Much like the cosmic microwave background provides a snapshot of the universe 380,000 years after the Big Bang, the neutrino background preserves a record from just 1 second after the beginning. Detecting it directly remains one of the ultimate goals of cosmology, but even indirect evidence of neutrinos' influence is already reshaping our understanding of the cosmos. Unlike photons or charged particles, neutrinos can traverse regions that are otherwise opaque. This makes them invaluable probes of extreme astrophysical events. For example, in 1987, the detection of neutrinos from supernova 1987A confirmed theories about how stars collapse and explode, with the particles arriving hours before the visible light. On a much grander scale, high-energy neutrinos detected by observatories like IceCube in Antarctica have been traced to distant blazes. Galaxies with supermassive black holes powering powerful jets. These detections link neutrinos directly to the most energetic accelerators in the universe. But neutrinos aren't just astrophysical messengers, they are cosmological players. Because they have tiny but non-zero masses, they influence how structure forms in the universe. Fast-moving neutrinos, sometimes called hot dark matter, stream out of small-scale density fluctuations, suppressing the growth of small structures while leaving larger ones intact. By measuring the distribution of galaxies and the Lyman-alpha forest, cosmologists can constrain the total mass of neutrinos. Current limits suggest their combined masses are less than about 0.1 to 0.2 electron volts. But even such tiny values have outsized effects on cosmic evolution. Detecting cosmic neutrinos is a daunting task because of their ghostly nature. They rarely interact with matter, so detectors must be enormous. Facilities like IceCube use a cubic kilometer of Antarctic ice, outfitted with sensors to detect the faint flashes of light produced when a rare neutrino collision occurs. Other experiments, such as Super Kamiokande in Japan and the upcoming Dune project in the US, use giant tanks of water or liquid argon deep underground. These detectors don't catch most neutrinos, only a tiny fraction of the countless particles that pass through them each second. But they still provide enough events to reveal cosmic patterns. High-energy neutrinos in particular are invaluable for understanding the far universe. Unlike cosmic rays, which are deflected by magnetic fields, neutrinos travel in straight lines. This means their arrival directions point back to their sources, letting us identify the astrophysical engines that produced them. And because they interact so weakly, they can cross billions of light-years without losing energy or being absorbed, making them true long-distance messengers. There is even more that neutrino astronomy can do. If we can directly find the cosmic neutrino background one day, it will give us a look into the very first second of the universe and let us study physics much earlier than the cosmic microwave background does. This might be possible someday thanks to new methods being worked on, like using very cold detectors to pick up the tiny rebound of atoms hit by relic neutrinos. If it works, neutrinos would become the oldest fossils we can see, which would change the field of astronomy. Particle physics has changed because of neutrinos. The fact that they change between different flavors, electron, muon, and tau neutrinos, showed that they must have mass, which was not what the standard model said they would have. This has given us new ways to look at basic physics, and made us think that neutrinos might hold answers to why matter and antimatter aren't balanced in the world. The extragalactic background light, EBL. A faint glow called the extragalactic background light, EBL, fills the universe. It is made up of light from every star that has ever shined, every galaxy that has ever formed, and every burst of cosmic action that has happened over billions of years. The cosmic microwave background is radiation that was around during the Big Bang. The EBL, on the other hand, is the radiation that has been gathered from all stars, galaxies, and quasars since the first ones were born. It is the afterglow of starlight in the universe, a soft background that holds the past of how stars were formed in the universe. The EBL spans wavelengths from the ultraviolet through the infrared, peaking in the optical and near-infrared regions. This makes sense. It's essentially the integrated starlight and dust reprocessed emission from galaxies across cosmic time. The ultraviolet and optical portion traces the direct light of stars, while the infrared portion arises when starlight is absorbed by dust and re-emitted at longer wavelengths. Together, the EBL provides a complete energy budget of how much light has been produced by structure in the universe. Measuring the EBL directly, however, is notoriously difficult. Our own galaxy, with its stars, gas, and dust, produces strong foreground emission that drowns out the faint extragalactic glow. The zodiacal light from dust in our solar system also adds contamination. Because of this, astronomers often rely on indirect methods. One of the most effective involves observing how high-energy gamma rays from distant quasars or blazars are absorbed as they travel through intergalactic space. Gamma rays interact with the EBL, producing electron-positron pairs and leaving a telltale cutoff in the gamma-ray spectrum. By measuring this attenuation with telescopes like Fermi-Leyte and Hess, scientists can estimate the intensity of the EBL across different wavelengths. What makes the EBL so valuable is that it serves as a cosmic fossil record of star formation. By comparing the intensity and spectrum of the EBL to models, astronomers can reconstruct how much light galaxies produced at different times in cosmic history. For example, the EBL confirms that the peak of star formation occurred around 10 billion years ago, redshift approximately 2, when galaxies were forming stars at rates far higher than they do today. Since then, star formation has gradually declined, leaving behind the quieter universe we see now. The EBL also offers insight into the role of dust in shaping galaxies. Dust grains absorb ultraviolet and visible light, then re-radiate it in the infrared. By studying the infrared portion of the EBL, astronomers can measure how much starlight has been hidden by dust and recover the full story of star formation, not just what we can see in optical telescopes. This helps bridge the gap between what telescopes like Hubble and JWST observe directly and what the universe has produced in total. Testing for new physics is another noteworthy way that EBL studies can be used. If gamma rays from very far away blazars stay alive at energies where EBL absorption should have killed them, it could mean that there are new particles or effects, like axion-like particles, changing into photons and back again. Even though these ideas are just guesses, the EBL is still one of the best places to study how the world reacts to high-energy radiation. Future missions and observatories promise to refine our picture of the EBL. The James Webb Space Telescope is already contributing by detecting faint galaxies that account for portions of the background. At the same time, upcoming gamma-ray observatories, like the Cherenkov Telescope Array, CTA, will extend our ability to measure EBL-induced absorption. Together, these tools will close the gap between direct and indirect measurements, giving us a clearer census of all the light ever emitted. The integrated Sachs-Wolfe effect. The world is not only getting bigger, dark energy is making it grow faster. This speeding up changes not only where galaxies are found and how bright supernovae are, but also how light from the cosmic microwave background, CMB, move through the universe's structure on a big scale. The integrated Sachs-Wolfe ISW effect is a subtle effect that is one of the few clear pieces of scientific proof for dark energy's effect on the universe. To understand the ISW effect, imagine a photon from the CMB crossing a large gravitational well, such as a galaxy cluster or a void. As the photon falls into the gravitational potential, it gains energy, a blue shift. On the way out, it loses energy, a redshift. So in a static universe, the net effect would cancel out. But in an accelerating universe, the gravitational potential itself changes while the photon is inside it. If the potential is decaying, the photon doesn't lose as much energy on the way out as it gained on the way in. The result is a tiny net energy shift. That small change manifests as slight temperature variations in the CMB, on the order of microkelvins. These variations are extremely subtle, but when correlated with the distribution of galaxies and matter, they become measurable. By comparing CMB maps with galaxy surveys, astronomers can detect the ISW effect statistically. CMB photons are slightly hotter in regions aligned with large-scale structures than they would be otherwise. The ISW effect has been measured using data from satellites like WMAP and Planck, combined with galaxy catalogues from surveys like the Sloan Digital Sky Survey, SDSS. These detections confirm that gravitational potentials are evolving in a way consistent with a universe dominated by dark energy. Without dark energy, or in a purely matter-dominated cosmos, the ISW effect would be absent or far weaker. There are actually two types of Sachs-Wolfe effects. The ordinary Sachs-Wolfe effect refers to the imprint of gravitational potentials at the surface of last scattering, essentially how the CMB was influenced by density variations when it was emitted. The integrated Sachs-Wolfe effect, by contrast, is the cumulative influence of changing gravitational potentials on CMB photons as they travel to us over billions of years. It is integrated because it builds up along the entire photon's path. The ISW effect is important because it can sense cosmic voids, as well as areas with too much matter. When photons move through big areas of low density, they have the opposite effect and come out a little cooler. By measuring the ISW imprint of voids, we can look at the spread of dark energy and see if our models of how the universe is speeding up are right. Some tests have shown that voids that are especially big might even be a cause of things like the CMB cold spot. The ISW effect is hard to study because it is so weak. There is a lot of noise around the ISW signal, but not around baryon sound pulses or supernova distances. Astronomers use cross-correlations between the CMB and galaxy studies to find the effect. Instead of looking for it directly in the CMB, they see if changes in temperature are statistically linked to the locations of large structures. We can be sure that the ISW effect is real because these relationships hold true across different datasets. Beyond testing dark energy, the ISW effect is also a probe of modified gravity theories. Different models of gravity predict different rates of potential decay and thus different ISW signatures. By refining measurements, cosmologists can test whether general relativity holds on the largest scales or whether alternative theories are needed. Time dilation in supernova light curves. They really mean it when they say that looking into deep space is like looking back in time. One of the best examples of this is supernova light curves, which show how the brightness of a supernova changes over time. If the world didn't change, the light would rise and fall the same way no matter how far away the explosion is. But time seems to be stretched because the universe is growing. This effect, called cosmic time dilation, makes supernova far away appear to spread slowly, with their light curves stretched by the same amount as their redshift. The principle is straightforward. If a nearby Type Ia supernova takes about 20 days to rise to maximum brightness, the same event observed at a redshift of z equals sign, one would take about 40 days from our perspective. The universe's expansion stretches not only the wavelengths of light, but also the passage of time for all observable events. Time dilation is thus a direct, measurable consequence of cosmological expansion, one that can't be explained away by alternative ideas like tired light. which suggest photons simply lose energy over distance without stretching time. Astronomers have confirmed this effect with remarkable precision. Surveys of distant type Ia supernovae have consistently shown that their light curves are broadened exactly as predicted by Redshift. The Supernova Cosmology Project and the High Z Supernova Search Team, the same groups that discovered cosmic acceleration, also demonstrated time dilation as a key confirmation of the expanding universe. Later surveys with the Hubble Space Telescope extended these measurements to even higher redshifts, leaving little doubt time dilation is real and it matches the predictions of general relativity. What makes this particularly powerful is that supernovae are among the few cosmic events bright enough to be studied in detail at large distances. Their predictable light curves make them ideal clocks for testing how expansion affects the flow of time. By comparing dozens or hundreds of supernovae across a range of redshifts, astronomers can build a timeline of how time dilation scales with distance, reinforcing the link between expansion, redshift, and the stretching of spacetime itself. Time dilation can also be used to test cosmic theories on its own. The link between redshift and time stretching would be different if the past of the universe's growth was different. The observations are very close to what the standard KCDM model says will happen, which gives us more faith that we're on the right track. With the cosmic microwave background, baryon acoustic waves, and galaxy clustering, this is yet another piece of proof that points to dark matter and dark energy being the main forces in the universe. Beyond type Ia supernovae, time dilation is also evident in other transient events. Gamma-ray bursts, for example, show statistical signatures of time stretching at high redshift. Quasars, too, exhibit variability patterns consistent with dilation, although these are harder to disentangle from intrinsic processes. Together, these phenomena extend the reach of time dilation studies beyond just one class of objects, making it a universal test of expansion. The fact that time dilation is so easy to understand is one of its best features. Time dilation is a simple effect that can be seen, unlike more abstract cosmological tools that need complicated models. Watch an explosion far away, time it, and then compare it to a close blast of the same type. The stretching is the same as the redshift, which makes sense if the world is growing. That's what it is, the universe showing us how it grows right in front of us. Surface brightness dimming. Astronomers see galaxies that are billions of light years away as smaller and redder than galaxies that are close by. They also see them as much fainter per unit area. This is known as surface brightness dimming, and it is a direct result of the universe expanding. It is a small but strong effect that makes it hard to look at the faraway galaxies, and at the same time is one of the strongest signs that space is growing. To understand surface brightness dimming, think of a galaxy as a patch of glowing pixels on the night sky. Its apparent brightness depends not just on how much total light it emits, but how much light arrives per unit of area on our detectors. In a static universe, brightness should decline with the inverse square of distance. Double the distance, and you get 1/4 the brightness. But in an expanding universe, there are extra effects at play. First, photons themselves are redshifted, stretched to longer wavelengths as they travel through expanding space. This means each photon carries less energy when it arrives. Second, because of time dilation, photons arrive less frequently than they would in a non-expanding universe. Finally, the apparent angular area of a distant galaxy is altered by cosmic geometry. Put together, these effects cause the observed surface brightness to scale as 1 + z4. At a redshift of z equals sine 1, a galaxy's surface brightness is already 16 times dimmer than expected in a static universe. At z equals sine 6, it's dimmer by a factor of over 2,000. This dimming has huge implications for observational astronomy. It explains why distant galaxies are so hard to detect, even with powerful telescopes. A galaxy at high redshift might be forming stars at a furious pace, but by the time its light reaches us, it appears as a faint diffuse smudge, barely distinguishable from the background. Without instruments like the James Webb Space Telescope, JWST, which can detect faint infrared light, many of these galaxies would remain invisible. Surface brightness dimming also provides a powerful test of cosmology. Back in the mid-20th century, some alternative models, like the so-called tired light idea, suggested that photons simply lose energy as they travel without the universe actually expanding. But tired light fails a key prediction. In an expanding universe, surface brightness, how bright an object looks per unit area, dims with redshift, following a very specific rule. It scales as 1 divided by 1 plus z to the 4th power. Observations of galaxies at different redshifts match this exactly, lining up with expansion and ruling out static models. It's one more nail in the coffin for the tired light hypothesis. Experts have a hard time telling the difference between natural faintness and global dimming. There are galaxies that really are small and faint at high redshift, and there are galaxies that are bright but look weak because of dazzle. By carefully modeling this, scientists can figure out what the real luminosities of galaxies far away were, and compare them to luminosities of galaxies today. These similarities show that early galaxies were, on average, smaller, denser, and made stars more quickly than galaxies do now. Surface brightness dimming also affects how we interpret galaxy morphology. Features like spiral arms, star-forming clumps, or extended halos are harder to see at high redshift, not necessarily because they weren't there, but because dimming erases low surface brightness features from our view. This means that galaxies we see in the early universe may look simpler or more compact than they actually were, simply because our instruments cannot pick up their faint outskirts. Correcting for this bias is essential for accurately reconstructing galaxy evolution. It can also be used to plan the construction of new telescopes. When astronomers plan studies, they have to take dimming into account and make sure that binoculars are sensitive enough to see the faint surface brightness of galaxies far away. This is why JWST was made as good as it could be, but even bigger telescopes, like the future Extremely Large Telescope, ELT, will be needed to see the faintest patterns at the edge of the universe that we can see. That surface brightness dimming so neatly connects fact and theory might be the most compelling aspect about it. Without math or complicated models, the universe shows that it is expanding by steadily making galaxies farther away less bright. Every dim galaxy at a high redshift is not only a challenge to observe, but also proof that space-time is stretching and carrying those photons over billions of years, dulling them as they go. The Tolman test of expanding space. In the early 20th century, as astronomers debated whether the universe was truly expanding or whether redshifts might have another explanation, one of the most elegant proposals came from Richard C. Tolman. He suggested a simple observational check, now called the Tolman surface brightness test, to distinguish between a static universe and one where space itself stretches. The principle is straightforward. If the universe is expanding, then the surface brightness of galaxies, their apparent brightness per unit angular area, should diminish not just with distance, but also with a distinct dependence on redshift. Tolman showed that in an expanding universe, surface brightness falls off as 1 divided by 1 plus z to the 4th power. This factor of 4 comes from several effects working together. First, photons are redshifted, so each one carries less energy by a factor of 1 plus z. Second, time dilation means photons arrive less often, adding another factor of 1 plus z. Finally, because an object's apparent angular size is stretched in an expanding universe, its observed area increases, adding 2 more powers of 1 plus z. Put all of this together, and the effect is dramatic. A galaxy at redshift 1 looks 16 times dimmer per unit area than it would in a static universe. At redshift 3, it looks 256 times dimmer. In models that don't grow, like the old tired light theory, photons just lose energy over distance, so the brightness of the surface would decrease much more slowly by only 1 plus z. This difference makes it easy to tell if the universe is really growing or not. Just look at how the light of galaxies changes with redshift. Carrying out the Tolman test, however, is not trivial. Galaxies evolve with time. their stars age, their star formation rates change, and their structures grow through mergers. To isolate the pure cosmological effect, astronomers must carefully correct for these evolutionary changes, as well as for observational biases like dust extinction and instrumental sensitivity. For decades, this made the Tolman test difficult to apply conclusively. It wasn't until the age of space telescopes, especially the Hubble Space Telescope, that Tolman's test could finally be carried out with the precision he had imagined. By observing galaxies across a wide span of redshifts and carefully accounting for how galaxies themselves evolve over time, astronomers confirmed the predicted dimming by 1 divided by 1 plus z to the 4th power. The results lined up exactly with the expectations of an expanding universe and decisively ruled out static alternatives. The Tolman test is important because it doesn't depend on the model. The Tolman test only looks at the geometry of growth, while more complicated probes need to guess about the amount of dark energy or matter present. It connects light to redshift directly without having to be checked against other stellar standards. Because it is so simple, it is a basic check on the idea of cosmic growth. Modern cosmology doesn't rely heavily on the Tolman test anymore, not because it's irrelevant, but because the evidence for expansion has become overwhelming from multiple other lines: the cosmic microwave background, Baryon acoustic oscillations, supernova distances, and galaxy clustering. Yet the Tolman test remains a beautifully direct demonstration. It shows that the universe itself encodes its expansion in the way distant galaxies appear fainter than intuition alone would predict. The Tolman test also remains a key consistency check in today's surveys. With instruments like the James Webb Space Telescope now able to spot galaxies at redshifts above 10, astronomers can apply the test to these ultra-distant objects as well. If their surface brightness strayed from the 1 divided by 1 plus z to the 4th law, it would hint at either exotic astrophysics or cracks in our cosmological model. But so far, the data keep lining up perfectly with Tolman's original prediction. The Tolman test also shows how creative early cosmologists were from a historical point of view. When the idea of the world growing was already a touchy subject, Tolman put forward a clear, logical way to settle the issue. His statement is still a cornerstone almost 100 years later, elegantly confirmed every time we find a faint galaxy at the edge of the universe that we can see. Light travel time versus look-back distance. Researchers use the term 10 billion light-years away to describe a galaxy. This phrase sounds simple, but in astronomy, distance is not a simple thing. Two things are different: look-back time, which is how long light took to get to us, and current distance, which is where that galaxy is. Due to the fact that the universe has been growing since the light's journey, the galaxy is now much farther away than the number of light-years it took to get there. One of the most important and least known parts of astronomy is the difference between light travel time and look-back distance. Let's start with look-back time. This is the interval between when the light left a distant object and when it arrived at Earth. For example, if we observe a galaxy whose light has been traveling for 10 billion years, its look-back time is 10 billion years. This measure is intuitive because it links distance directly to time. We are literally seeing that galaxy as it was 10 billion years ago, when the universe was much younger. Look-back time is why astronomers often say looking far away means looking back in time. But the actual distance to that galaxy today is not 10 billion light-years. During those 10 billion years of travel, space itself expanded, carrying the galaxy much farther away. The proper distance to that galaxy right now might be more like 25 or even 30 billion light-years, depending on its redshift. This is called the co-moving distance, the distance accounting for the stretching of space. For the edge of the observable universe, the difference is even more dramatic. The cosmic microwave background comes from photons that have been traveling for 13.8 billion years, but the region they came from is now about 46 billion light-years away. This is why cosmologists define several different kinds of distance, each useful in its own way: light travel distance, or look-back time, tells us how long the light from an object has been on its journey to reach us. Proper distance is the distance to the object at a specific moment in cosmic time. Comoving distance is the proper distance today, with cosmic expansion factored in. Angular diameter distance compares how large an object looks in the sky to its true physical size. And luminosity distance compares how bright an object appears to us with how bright it actually is. These definitions may be hard to understand, but they are necessary for properly interpreting data. A galaxy that gave off light 12 billion years ago can be seen at a redshift of about 4. It takes 12 billion light years for light to reach that far, but now it takes more like 26 billion light years. If this difference isn't made, comments about how far away galaxies are might not be accurate. The difference between look-back and co-moving distances is not just a semantic issue, it's fundamental to cosmology. It explains why the observable universe has a radius of 46 billion light-years, not 13.8 billion. It also underlies why some galaxies we can see today are already beyond our cosmic event horizon. Their light left them long ago, but because of accelerating expansion, any light they emit now will never reach us. Understanding these distances also helps with planning observations. For instance, when we observe galaxies with JWST at redshifts of 10 or higher, we're seeing them as they existed only a few 100 million years after the Big Bang. But those galaxies are not a few 100 million light-years away. Their present-day co-moving distances are tens of billions of light-years, showing just how much the universe has stretched since their light began its journey. For non-specialists, this can be counterintuitive. We often think of distance as a fixed, measurable line between 2 points. But in an expanding universe, distance is dynamic. Space itself changes, stretching while photons traverse it. Light travel time gives us a direct connection to the past. Co-moving distance tells us where those objects are now. Both are valid, but they answer different questions. The visibility of structures beyond the CMB. Light can only take us back so far. The cosmic microwave background, CMB, is the last light from the Big Bang, which happened about 380,000 years after the universe began. After that, the universe was a hot, cloudy plasma of protons and electrons that constantly scattered photons. In the past, light just couldn't move around easily. So the CMB is a cosmic wall, the farthest electromagnetic wave that we can directly see. That doesn't mean, though, that the older world will always be hidden. We might be able to see past the CMB and into times we've only thought about in theory if we have senders other than photons. The problem with photons before recombination is opacity. In the early plasma, photons scattered constantly off free electrons through a process called Thomson scattering. This prevented light from traveling more than a short distance before being deflected. Only when the universe cooled enough for electrons to combine with protons into neutral hydrogen did the fog lift, allowing photons to stream freely and giving us the CMB. Anything earlier in time remains invisible to light, but photons aren't the only cosmic messengers. One alternative is the cosmic neutrino background, CNB, a sea of relic neutrinos that decoupled from matter just 1 second after the Big Bang. Unlike photons, neutrinos barely interact with matter, so they slipped free long before recombination. Detecting them directly would let us probe the universe's state mere seconds after it began. While the CNB has not yet been observed directly, its existence is strongly supported by Big Bang nucleosynthesis and cosmological models. Experiments like Ptolemy aim to measure it, potentially opening a new window beyond the CMB. Gravitational waves are another way that the door could be opened. Gravitational waves, which are ripples in space-time, can pass through matter almost without being stopped, just like photons can be spread out. Gravitational waves that were made during inflation could make a primordial background that holds data from the very first fractions of a second after the Big Bang. The CMB marks the end of the opaque age, but this stochastic gravitational wave background would come from a lot earlier, giving us a straight look into the physics of inflation. To find these old ripples, experiments like LISA, Laser Interferometer Space Antenna, and pulsar timing arrays are being built. We can also study conditions before the CMB by looking at their imprints on later signals. For example, the CMB itself carries traces of physics from the first few minutes, such as the density of baryons and neutrinos. Similarly, the distribution of light elements like helium and deuterium, forged in Big Bang nucleosynthesis, reflects conditions in the first minutes of cosmic history. These relics, while not direct images, provide evidence of epochs hidden behind the photon fog. In theory, the first structures we could look into without using photon messages would be changes in density caused by inflation. The cosmic web we see today was started by these changes, and you can still see their marks in the CMB's anisotropies and the way galaxies are spread out on a big scale. We could see farther back than photons can if we could find them using neutrinos or gravity waves. This would allow us to observe events that happened almost at the start of time. Even so, it's important to stress that no electromagnetic camera, no matter how strong, will ever be able to see past the CMB. Photons can't go past that distance. We need to use more than one signal to look into what's beyond, which would make astronomy a truly multi-signal study. Foreground contamination in cosmic maps. Scientists have a hard time mapping the universe's oldest signals, like the cosmic microwave background, CMB, the extragalactic background light, or the faint glow of neutral hydrogen at 21 centimeters. This is because the universe is full of surrounding noise. The Milky Way, other galaxies nearby, dust, and even pollution from Earth can all send out unwanted messages that can block out the very faint voice of the early universe. One of the biggest problems in observed cosmology is that the foreground can get messed up. Take the CMB as an example. The CMB itself has an average temperature of just 2.7 Kelvin, with tiny fluctuations at the level of tens of microkelvins. But our Milky Way produces strong microwave emission from dust grains, synchrotron radiation from charged particles spiraling in magnetic fields, and free radiation from ionized gas. These galactic emissions are often orders of magnitude stronger than the CMB anisotropies researchers want to measure. Without careful separation, the Milky Way's signal would completely overwhelm the CMB's delicate structure. To deal with this, cosmologists rely on multi-frequency observations. Different foregrounds dominate at different wavelengths, synchrotron at low frequencies, dust at high frequencies. By observing the same patch of sky in many frequency bands, missions like Planck and WMAP can model and subtract the foregrounds, leaving behind the true CMB signal. This process, called foreground cleaning, is mathematically complex but essential for extracting cosmological information. If you use 21 centimeter cosmology, the situation is even worse. Galactic foregrounds that can be 10,000 times stronger hide neutral hydrogen signals from the cosmic dark ages. These signals are very weak. In addition, radio signals from people like cell phones and satellites mess up the bands that are important. Hydrogen Epoch of reionization array, HERA, projects and the Future Square Kilometre Array, SKA, will need to use smart statistical methods to separate the weak cosmological signs from the background noise. As an example, the foregrounds tend to have smooth spectral edges, while the 21 cm signal has clear changes. The difference can be used to help experts figure out things about the universe. Even optical and infrared surveys are not immune. When astronomers try to measure the extragalactic background light, EBL, they must contend with the zodiacal light, sunlight scattered off dust in our own solar system, which can outshine the faint glow of distant galaxies. Likewise, dust in the Milky Way reddens and dims the light from background galaxies, complicating efforts to measure their true brightness. In every wavelength, local contamination threatens to obscure the universe's deeper signals. Foregrounds aren't just nuisances. They can also mimic or distort cosmological features if not handled properly. For example, galactic dust polarization can imitate the signal of primordial gravitational waves in the CMB's polarization pattern. In 2014, the BICEP-2 experiment initially announced a detection of such a signal, only to later discover that it was largely due to foreground dust. That episode highlighted how vital it is to separate cosmic signals from local contamination before drawing revolutionary conclusions. Scholars are coming up with ever more advanced methods to deal with these problems. Cleaning up data can be done with statistical models, cross-correlation with separate datasets, and machine learning. Observatories are also built in remote places, like mountains, high plateaus, or even space, so that human activity doesn't get in the way. Building radio telescopes on the far side of the Moon, away from Earth's noise, could be the next big thing. These would be able to pick up messages from the very beginning of time. Foreground contamination is a steady warning that astronomy isn't really done in a vacuum. Every signal we're looking for is buried under a layer of local noise, and it takes both creativity and patience to get to the signal below. But the return is huge. The pictures of the CMB, the 21 cm signal, or the cosmic web, are some of the most useful scientific records once they have been cleaned up. They show conditions that happened billions of years ago. JWST's reach into the early universe. The James Webb Space Telescope, JWST, has changed the way we look at the world far away. Because it was made to look at infrared light, it can find light from the very first galaxies, light that has been stretched into longer bands by the expansion of the universe. The Hubble Space Telescope let us see galaxies with redshifts of about 10. The James Webb Space Telescope, JWST, is already going further, catching galaxies that may have formed less than 300 million years after the Big Bang. Why infrared? Because as the universe expands, photons emitted in the ultraviolet or visible bands are redshifted into the infrared. JWST's instruments, particularly NIRCam, near-infrared camera, and NIRSpec, near-infrared spectrograph, were built specifically to capture this ancient, stretched light. Its 6.5-meter primary mirror collects more light than Hubble's 2.4-meter mirror, making it sensitive enough to detect faint galaxies billions of light-years away. In its first year of observations, JWST stunned astronomers by detecting candidates for galaxies at redshifts greater than 13. That means we are seeing them as they existed just a few 100 million years after the Big Bang. These galaxies appeared brighter and more massive than expected, challenging some models of how quickly structures could form. While follow-up spectroscopy is confirming which of these candidates are truly that distant, the discoveries have already reshaped theories of early galaxy formation. JWST is not only finding galaxies, but also probing their composition and structure. Its spectrographs can detect emission lines from hydrogen, oxygen, and other elements, revealing how enriched these young galaxies were with heavy elements. The data suggest that star formation and chemical enrichment happened remarkably fast, with some galaxies showing signs of multiple generations of stars, even within the first 500 million years. This challenges the idea that the early universe was dominated solely by pristine, metal-free stars. Another important thing that JWST can do is study the epoch of reionization. This is the time when the first galaxies and quasars charged the hydrogen gas that filled the universe. JWST is helping us figure out how and when reionization happened by measuring the light that early galaxies let go of, and the parts of their spectra that are absorbed. In between the cosmic dark ages studied by 21 cm cosmology and the later, more developed galaxies seen by Hubble, it acts as a link. Beyond galaxies, JWST is detecting some of the earliest black holes. Its observations have revealed quasar candidates powered by supermassive black holes less than 1 billion years after the Big Bang. How such massive black holes grew so quickly remains one of the great puzzles in astrophysics. JWST's data may help determine whether they formed from the direct collapse of massive gas clouds, the rapid growth of stellar mass black holes, or other exotic processes. JWST also excels at studying gravitational lensing, where massive galaxy clusters magnify the light of even more distant galaxies behind them. Programs like the Frontier Fields use this natural magnification to push JWST's reach further, revealing faint galaxies that would otherwise be invisible. In some cases, lensing allows astronomers to study galaxies at redshifts of 15 or beyond, effectively using the cosmos itself as a telescope. The telescope's role in early universe cosmology is complemented by its capacity for wide surveys. Large programs are cataloging thousands of galaxies at redshifts between 6 and 12, providing the statistical power to study galaxy evolution across cosmic dawn. These datasets will help answer fundamental questions. How fast did galaxies grow? How did star formation proceed in the first billion years? And what role did galaxies play in reionizing the universe? Even though JWST wasn't made just for cosmology, it also studies exoplanets, star nurseries, and other things. It has already had a huge effect on how we think about the beginning of the universe. It has pushed the limits of what we can see in the universe for galaxies and quasars, giving us straight pictures and spectra from times we thought were out of reach. Gravitational lensing as a cosmic telescope. Astronomers find gravitational lensing to be one of the coolest tricks the universe can play on them. Einstein's general theory of relativity predicted that lensing would happen when a large object, like a collection of galaxies, bends the path of light from farther away objects behind it. Because of this, the object in the background can look like it has been stretched, warped, repeated, or even blown up into arcs and rings. Cosmologists don't just find gravitational lensing interesting. They see it as a cosmic telescope that lets us see galaxies that would be too small or far away to see directly otherwise. There are two main flavors of lensing. Strong lensing happens when the alignment between the lens and the background source is precise. This produces dramatic features like Einstein rings or giant arcs, where the background galaxy is magnified many times over. These magnifications allow astronomers to study details of early galaxies, such as star-forming clumps or chemical compositions that would be invisible without the natural boost. Some of the most distant galaxies known have been discovered thanks to strong lensing by massive galaxy clusters. Weak lensing, on the other hand, is more subtle. Here, the shapes of many background galaxies are distorted slightly, stretched in a preferred direction by intervening mass. By analyzing these distortions statistically across millions of galaxies, astronomers can map the distribution of dark matter and measure how structure has grown over cosmic time. Weak lensing has become one of the most powerful tools for constraining dark energy, since the growth of structure depends sensitively on the universe's expansion history. One of the most famous applications of strong lensing is the Hubble Frontier Fields program, where the Hubble Space Telescope used massive galaxy clusters as natural magnifying glasses. This strategy revealed galaxies at redshifts greater than 10, pushing the observable boundary of cosmic dawn. Now, JWST is continuing this work, capturing even more detailed images of lensed galaxies and confirming their extreme distances. Without lensing, many of these galaxies would simply be beyond our reach. Gravitational lensing is not only useful for observing faint galaxies, it also provides unique tests of physics. The precise distortions and time delays between multiple images of a lensed quasar, for example, can be used to measure the Hubble constant, providing an independent check on other methods. Lensing also allows astronomers to probe the substructure of dark matter halos, since small clumps of dark matter affect the way lensed images are distorted. This makes it one of the only direct methods of studying dark matter on small scales. Microlensing is another new area of study. This is when a star or even a planet moves in front of background sources and changes their shape. Microlensing is studied most often in terms of exoplanets in the Milky Way, but it is also important in extragalactic astronomy and can sometimes change how bright lensed quasars are. In theory, it could even show groups of compact dark matter objects, such as primitive black holes if they exist. The power of gravitational lensing lies in its ability to turn the cosmos into its own observatory. Instead of building ever larger telescopes, astronomers can exploit the universe's natural geometry to magnify light from the farthest sources. It's a synergy between nature and technology. Our instruments detect the signal, but space-time itself provides the magnification. Gravitational lensing of the CMB. The cosmic microwave background, CMB, shows us a picture of the universe that is almost as good as new from only 380,000 years ago. But the photons that make up the CMB didn't come to us on tracks that were straight and smooth. Many billions of galaxies, clusters and strands of dark matter were in their path over the course of 13.8 billion years. Each of these huge objects slightly bent the photons through gravity lensing, which changed the way the CMB looked in small ways. Astronomers can make maps of dark matter, the unseen stuff that holds the universe together, by looking at these distortions. As CMB photons pass through varying gravitational potentials, their paths are deflected by tiny amounts, typically a few arc minutes or less. This doesn't produce dramatic arcs like galaxy lensing, but instead smoothly remaps the CMB's delicate pattern of temperature fluctuations. Peaks and troughs in the CMB are shifted, blurred, and correlated in ways that wouldn't exist without lensing. Extracting this information requires advanced statistical analysis, but it unlocks a three-dimensional map of mass distribution between us and the surface of last scattering. The Planck satellite made one of the first big steps forward by making maps of the whole sky that showed how the CMB lensing could work. Along with studies of galaxies, these maps showed where dark matter was spread out on a large scale, up to redshifts of about 2. CMB lensing reacts to all matter, whether it is bright or dark. Galaxy clustering only tracks matter that is glowing. It is one of the best ways to learn about the cosmic web because of this. CMB lensing is especially important for studying neutrino masses. Because neutrinos move quickly and suppress structure formation on small scales, their masses leave a detectable imprint on how strongly the CMB is lensed. By combining CMB lensing with galaxy surveys, cosmologists have placed some of the tightest limits yet on the sum of neutrino masses, currently below about 0.1 to 0.2 electron volts. In other words, the faint distortions in the afterglow of the Big Bang tell us about one of the lightest and most elusive particles in physics. It can also be used to improve measures of dark energy. How structure has grown over time depends on how the universe has grown over time. Cosmologists can see how that growth is happening and see if dark energy acts like a constant or more like something that changes over time by comparing lensing maps made at different redshifts. Soon, studies will use both CMB lensing and weak galaxy lensing to make maps of how mass is distributed across cosmic time. These maps will put more limits on dark energy models. CMB lensing also helps cosmologists clean other signals. For instance, one of the key goals in cosmology is to detect primordial gravitational waves from inflation, which would leave a distinctive B-mode polarization pattern in the CMB. But lensing of the CMB by large-scale structure can also generate B-modes, acting as a contaminant. By mapping lensing accurately, researchers can subtract its contribution, a process called delensing, to reveal the primordial signal beneath. This makes CMB lensing not just a science target, but also a crucial calibration tool. New telescopes, such as CMB-S4 and LightBird, will make it possible to measure CMB lensing with even more accuracy. Ground-based projects like the South Pole Telescope and the Atacama Cosmology Telescope are already improving maps of lensing with a precision of 1 arcminute. This makes it possible to rebuild the distribution of dark matter with great accuracy. When put together with data from JWST and galaxy studies like DESI and Euclid, these datasets will give us a full picture of how structures are formed all over the universe. Polarization patterns in the CMB. The cosmic microwave background, CMB, is not just a faint glow of ancient light. It is also polarized. Like sunlight scattered off Earth's atmosphere becomes partially polarized, the last scattering of photons by electrons 380,000 years after the Big Bang produced a subtle polarization pattern imprinted on the CMB. Measuring this polarization has become one of the most powerful tools for cosmologists, revealing details about the early universe that temperature maps alone cannot provide. Polarization in the cosmic microwave background comes in 2 main forms, E modes and B modes. E-modes are curl-free patterns, like the way light scatters from a perfectly round source. They are mostly produced by density fluctuations in the early plasma. Satellites like WMAP and Planck have measured E-modes with great precision, and the results match the predictions of the standard LCDM model almost perfectly. These measurements give us independent confirmation of the same physics that shape the CMB's temperature fluctuations, which strengthens our confidence in the standard cosmological model. B-modes, by contrast, are curl-like patterns and much harder to detect. They can arise in two ways. First, from gravitational lensing, where large-scale structures in the universe bend E-modes into B-modes. Second, and more exciting, from primordial gravitational waves produced during cosmic inflation. Detecting these primordial B-modes is considered one of the holy grails of cosmology, because it would give direct evidence for inflation and open a window into physics at energy scales far beyond what any particle accelerator could reach. The search for B-modes has already produced moments of high drama. In 2014, the BICEP-2 experiment at the South Pole announced the detection of B-modes consistent with inflationary gravitational waves. The result made global headlines. But further analysis showed that galactic dust foregrounds could account for most, if not all, of the signal. The episode highlighted just how careful astronomers must be when separating faint cosmic signals from contamination. Since then, experiments like PolarBear, SPT-Pol, and BICEP-Keck array have steadily improved sensitivity, providing better maps of both lensing-induced and potential primordial B-modes. Polarization patterns are also vital for studying reionization, the epoch when the first stars and galaxies ionized the intergalactic medium. Reionization left its mark on the CMB by scattering photons once again, producing polarization at large angular scales. Measuring this large-scale polarization allows cosmologists to pin down when reionization occurred, offering crucial insight into the timeline of the first galaxies and quasars. CMB polarization helps refine estimates of key cosmological parameters. For instance, E-mode data constrain the optical depth of reionization, the density of baryons, and the tilt of the primordial power spectrum. By combining polarization data with temperature maps, cosmologists can break degeneracies between parameters, improving the precision of the overall cosmological model. Detecting primordial B-modes is one of the biggest goals in cosmology for the coming decades. A confirmed signal wouldn't just prove that inflation happened, it would also reveal the energy scale of inflation itself, around 10 to the 16th giga-electronvolts. That's a level of energy completely beyond anything human technology could ever reach. Such a discovery would connect cosmology and particle physics at their deepest levels, offering a direct glimpse into physics at the dawn of the universe. To get there, polarization is at the center of plans for future projects like LIGHTBIRD and CMBS-4, as well as ground-based telescopes at the South Pole and in Chile's Atacama Desert. They want to separate the weak B-mode signal from things like galactic dust, synchrotron emission, and lensing by recording the sky at many frequencies and with great accuracy. It is also very important to make progress in delensing methods, which remove the lensing effect to focus on primordial B-modes. The cosmic event horizon. There is an end to every trip, and the cosmic event horizon marks the end of the world that we can see. The event horizon, on the other hand, marks the farthest point from which light will never be able to reach us, no matter how long we wait. The particle horizon marks the farthest point from which light has reached us since the Big Bang, not just a limit of the technology or devices we have now, but also a limit set by the way the universe expands itself. The event horizon arises because the universe is expanding at an accelerating rate, driven by dark energy. This means that distant galaxies are receding faster and faster as time goes on. For those far enough away, the expansion is so rapid that even light emitted toward us now will never make it. Instead, the light gets carried away with the expansion, redshifted into oblivion. These galaxies are not just invisible today, they are forever beyond reach, sealed off by the cosmic event horizon. The mathematics is striking. In the standard LCDM cosmology, the event horizon lies at about 16 billion light-years from Earth. This means that while the particle horizon, the edge of the observable universe, extends out to about 46 billion light-years, only objects within 16 billion light-years can ever send us new signals in the future. Everything beyond that is effectively lost to us, not because it doesn't exist, but because the expansion of the universe outpaces the ability of light to bridge the gap. This has very important effects on the future of the world we can see. The event horizon will be crossed by more and more galaxies over time. Already, galaxies with redshifts higher than about 1.8 are expanding and moving away from us, faster than light. They gave off light a long time ago, so we can still see them. But any new light they give off now will never get here. Over a very long time, only the Milky Way, Andromeda, and their satellites will still be visible because they are gravitationally tied to our local group. The rest of the world will get darker. The event horizon also sets limits on what cosmology can ever achieve. Even with infinite time and perfect instruments, we will never observe directly what happens beyond this boundary. It is the ultimate horizon, a reminder that our window into the cosmos is not infinite. The structures, galaxies, and possible civilizations that lie beyond it are permanently cut off from us, no matter how advanced our science becomes. We still have a lot to learn about that future, though. The limit of 16 billion light-years includes hundreds of billions of galaxies, trillions of stars, and a number of planets that are almost impossible to count. Even though the event horizon makes it harder to see into the future of the universe, it also creates a unique laboratory in space that is full of interesting things for generations of scientists to study. We've been to the very edge of what the universe lets us see, from the first sounds of hydrogen to the farthest galaxies made bigger by gravity. We've even caught a glimpse of the borders we'll never cross. But this is only the first step into the unknown. Please like, subscribe, and join us here on Beyond Horizons for more journeys into the universe. Also, don't miss our next video. We'll be pushing into a new territory that will change the way you see the universe.